Hello there, and welcome to Sleep Science Chronicles. Tonight, we turn our gaze toward one of the gentlest fates the universe has to offer. We will spend these quiet hours exploring white dwarfs, the soft, glowing embers left behind when stars like our sun reach the end of their long lives. There's no explosion in this story. No violent collapse into darkness. Instead, there's patience, a slow release, a dimming that unfolds across timescales so vast that the entire history of human civilization would vanish within them, like a single breath. White dwarfs are among the most common stellar remnants in the cosmos, yet they are easy to overlook. They do not blaze across the sky or announce themselves with bursts of radiation. They simply exist, small, dense, and impossibly ancient, cooling quietly in the dark like coals left over from a fire that burned for billions of years. Tonight we will follow the journey that leads to these quiet embers. We will watch stars swell and shed their outer layers, leaving behind glowing cores no larger than the Earth, but carrying the mass of the Sun. We will explore what happens inside these strange objects, where matter is crushed so tightly that a teaspoon would weigh as much as an elephant. We will trace their cooling over trillions of years, long after every other light in the universe has faded. And perhaps along the way, you will find yourself drifting into rest. That is perfectly fine. These facts will be here, waiting in the dark, whether you hear them or not. Let your breath slow. Let your shoulders soften. And let the quiet story of dying stars carry you gently towards sleep. The universe is filled with violence. Stars explode. Galaxies collide. Black holes tear matter apart at the edge of oblivion. But not everything ends in catastrophe. Some endings are gentle. Some are patient. Some unfold so slowly that the word ending hardly seems to apply. White dwarfs represent one of these quiet conclusions. They are the final stage for stars that are not massive enough to collapse into neutron stars or black holes. Stars like our own sun, and the vast majority of stars scattered across the Milky Way. When these stars exhaust their fuel, they do not detonate. They do not implode. They simply let go. The outer layers drift away into space, forming shells of glowing gas that astronomers call planetary nebulae, some of the most beautiful objects in the cosmos. And at the center, the core remains, exposed, compressed, glowing white hot from the heat of billions of years of nuclear fusion, but no longer generating any new energy, just radiating, just cooling, just waiting. A white dwarf is not quite alive and not quite dead. It is something in between, a stellar afterglow, a remnant warmth, a memory of the star that once was. And it will remain in this state for longer than the universe has currently existed, cooling so slowly that by the time it finally fades, the cosmos around it will be unrecognizable. Tonight, we will explore this quiet world. We will learn how white dwarfs form, what they are made of, and what strange physics governs their existence. We will discover how they crystallize into cosmic diamonds, how they sometimes reignite in brilliant flashes, and how they serve as some of the most precise clocks in the universe. And we will look ahead to the far future, when white dwarfs will be among the last sources of warmth in a darkening cosmos. This is not a story of drama. It is a story of patience, of endings that are not really endings, of light that fades so slowly it almost seems eternal. Let yourself settle into this journey. There is no rush. the white dwarfs have been waiting for billions of years. They can wait a little longer while you find your rest. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest. Let your mind soften. Let's begin. Stars are born in clouds of gas and dust called nebulae. These clouds drift through galaxies for millions of years, seemingly inert, until something disturbs them. Perhaps a nearby supernova sends a shock wave rippling through the cloud. Perhaps the gravitational influence of a passing star tugs at its edges. Whatever the cause, the disturbance creates regions of higher density, and gravity begins to take hold. Matter pulls toward matter. The cloud begins to collapse. As the cloud contracts, it heats up. The center grows denser and hotter, and eventually, a core forms. A protostar, not yet capable of fusion, but glowing with the heat of gravitational compression. This is the embryonic stage of a star, a gathering of matter that has not yet ignited, but is well on its way. The protostar continues to accumulate material from the surrounding cloud, growing larger and hotter with each passing millennium. When the core of a protostar reaches temperatures of about 10 million degrees, hydrogen nuclei begin to fuse into helium. This is the moment of ignition, the birth of a true star. The energy released by fusion creates an outward pressure that balances the inward pull of gravity, and the star settles into a long, stable existence. For a star like our Sun, this stable phase will last approximately 10 billion years. During this time, the star burns hydrogen in its core at a remarkably steady rate. The process is not combustion in the chemical sense. Nothing is catching fire. Instead, nuclear fusion combines 4 hydrogen nuclei into a single helium nucleus, releasing a small amount of mass as pure energy according to Einstein's famous equation. This energy radiates outward, providing the light and heat that warm any planets orbiting nearby. The rate at which a star burns through its hydrogen depends on its mass. More massive stars have stronger gravity, which compresses their cores to higher temperatures and pressures. This causes fusion to occur more rapidly, and the star burns through its fuel much faster. A star 10 times the mass of the Sun might exhaust its hydrogen in only a few tens of millions of years. But stars like the Sun, modest in mass, gentle in temperament, burn slowly. They are not in a hurry. They have billions of years stretching ahead of them, and they spend that time in a state of peaceful equilibrium. The Sun has been burning for about 4.5 billion years, and it has roughly another 5 billion years of hydrogen fusion remaining. Halfway through its life, it is a middle-aged star still glowing steadily, still warming the Earth. The hydrogen that fuels a star is not distributed evenly throughout its interior. Fusion occurs only in the core, where temperatures and pressures are high enough to overcome the natural repulsion between positively charged hydrogen nuclei. The outer layers of the star are cooler and serve mostly as an envelope, pressing down on the core and keeping it compressed. As the star ages, the core gradually becomes enriched with helium, the ash of hydrogen fusion. This helium is denser than hydrogen and sinks toward the center, forming a growing helium core. The hydrogen-burning region slowly migrates outward, forming a shell around the helium core where fusion continues. This transition marks the beginning of the end. Though it unfolds so slowly, that billions of years may pass before the changes become dramatic. Stars like the Sun exist in a delicate balance between two opposing forces. Gravity pulls the star's mass inward, trying to compress it into an ever smaller volume. Meanwhile, the energy generated by nuclear fusion creates an outward pressure that resists this compression. For most of a star's life, these forces are perfectly matched, and the star maintains a stable size. This equilibrium is not static. It is dynamic. The star is constantly adjusting, with small fluctuations in fusion rate leading to small changes in pressure and temperature. But these variations are minor, and the overall structure remains steady. The Sun today looks almost identical to the Sun a billion years ago, and it will look much the same a billion years from now. Stability in the stellar sense means change so gradual it is nearly imperceptible. The light from a star like the Sun takes time to reach the surface. Energy generated in the core does not travel outward in a straight line. It bounces, scatters, and is absorbed and re-emitted countless times by the dense material of the star's interior. A photon born in the Sun's core may take tens of thousands of years to reach the surface, zigzagging through the dense plasma in a random walk that covers only a short distance with each step. Once that energy finally reaches the surface, it escapes into space as light. The journey from core to surface takes far longer than the journey from the Sun to Earth, which light covers in just over 8 minutes. The warmth you feel on a sunny day began as a fusion reaction deep in the solar core long before human civilization existed. Stars do not burn uniformly throughout their lives. As they age, subtle changes occur. The core contracts slightly as helium accumulates, and this contraction causes the core to heat up. The increased temperature causes fusion to occur at a slightly higher rate, which makes the star gradually brighter over time. The Sun today is about 30% brighter than it was when it first formed 4.5 billion years ago. This gradual brightening has implications for any planets orbiting the star. Earth has remained habitable for billions of years, in part because of feedback mechanisms in the climate system that have compensated for the Sun's increasing luminosity. But this balance cannot hold forever. In roughly 1 billion years, the Sun will be bright enough to evaporate Earth's oceans, regardless of any natural or artificial intervention. The concept of a star's lifetime can be misleading. When astronomers say the Sun has 5 billion years of fuel remaining, they mean 5 billion years of core hydrogen fusion. But this is not the end of the star. It is the end of one phase. After the core hydrogen is exhausted, the star will continue to exist for hundreds of millions of years more, undergoing dramatic transformations before finally settling into its quiet end. The distinction matters because it shapes our expectations. A star does not simply switch off when its fuel runs out. It changes, it swells, it sheds, it becomes something new. The white dwarf at the end of this journey is not the same object as the main sequence star that preceded it. Yet, there is continuity. The same matter, the same core, transformed by time and physics into a different kind of existence. Most stars in the universe are smaller than the Sun. Red dwarfs, which make up roughly 70% of all stars, have masses between about 8 and 50% of the Sun's mass. These tiny stars burn their hydrogen so slowly that their lifetimes stretch into the trillions of years, far longer than the current age of the universe. No red dwarf has ever died of old age. The universe is simply not old enough. Stars larger than the sun are rarer, but far more luminous. A star with 3 times the sun's mass might shine 50 times brighter, but it will exhaust its fuel in only a few 100 million years. The most massive stars, with dozens of times the sun's mass, burn so fiercely that they live for only a few million years before exploding as supernovae. The stellar lifespan is inversely related to mass. The bigger the star, the shorter its life. The sun and stars like it occupy a middle ground. Not so small that they will burn forever. Not so massive that they will explode. They are modest stars, destined for modest ends. After billions of years of steady burning, they will swell, shed their outer layers, and leave behind dense, cooling cores. No supernova, no black hole. Just a quiet transition from one state to another. A gentle passage from life to afterlife. This is the fate that awaits the sun, and it is the fate that has already claimed countless stars across the galaxy. The white dwarfs scattered through the Milky Way are the remains of stars that once shone as brightly as the sun does now. They are ancient, they are patient, and they are still glowing even now, with the residual heat of lives that ended billions of years ago. When a star like the sun exhausts the hydrogen in its core, fusion does not stop entirely. Instead, it migrates outward, continuing in a shell surrounding the now inert helium core. This shell-burning phase produces energy at a higher rate than core fusion did, and the excess energy causes the outer layers of the star to expand. The expansion is dramatic. The sun, currently about 1.4 million kilometers in diameter, will swell to roughly 200 million kilometers, large enough to engulf the orbits of Mercury and Venus, and possibly Earth as well. The surface will cool as it expands, shifting in color from yellow-white to orange, and then to red. This is the red giant phase, named for the star's bloated size and cooler surface temperature. Inside a red giant, the structure is far more complex than in a main sequence star. The core is made of helium, compressed to extraordinary density by the weight of the overlying layers. Surrounding the core is a thin shell where hydrogen continues to fuse into helium, releasing energy. And beyond that shell lies an enormous envelope of gas, extending outward to distances that dwarf the original star. The helium core is not fusing, not yet. It is simply sitting there, growing heavier as more helium ash falls onto it from the hydrogen-burning shell above. The core is supported against gravitational collapse, not by fusion energy, but by a quantum mechanical effect called electron degeneracy pressure. This is a preview of what will eventually support the white dwarf itself. The red giant phase can last for hundreds of millions of years, though this varies depending on the star's mass. During this time, the star's outer layers become increasingly loosely bound. The surface gravity is much weaker than it was during the main sequence phase, because the same mass is now spread across a much larger volume. Particles in the outer atmosphere can escape more easily, carried away by stellar winds. This mass loss is significant. A red giant may shed a substantial fraction of its original mass over the course of this phase, with material drifting away into space at velocities of tens of kilometers per second. The stellar wind is not dramatic. It is a slow, steady outflow, a gentle hemorrhage that gradually reduces the star's mass over millions of years. As the helium core grows, it also contracts and heats up. Eventually, the core reaches a temperature of about 100 million degrees. hot enough for helium to begin fusing into carbon. This ignition does not occur gradually. In stars like the Sun, the helium core is degenerate, meaning its pressure does not depend on temperature. When fusion begins, the energy released does not cause the core to expand and cool as it would in a normal gas. Instead, the temperature rises further, accelerating fusion in a runaway process. This event is called the helium flash. It occurs deep within the star, hidden from view by the overlying layers. The energy released is enormous. For a brief moment, the core generates more power than an entire galaxy. But almost all of this energy is absorbed by the star's interior, going into lifting the degeneracy of the core and expanding it. From the outside, the star shows little change. The helium flash is a silent convulsion, a hidden drama. After the helium flash, the core settles into a new equilibrium. Helium is now fusing steadily into carbon and oxygen in the core, while hydrogen continues to burn in a shell around it. The star contracts somewhat from its maximum red giant size, though it remains far larger than it was on the main sequence. This phase is relatively short-lived, only about 100 million years for a star like the Sun. The carbon and oxygen produced by helium fusion accumulate in the center of the core, forming a growing carbon-oxygen core surrounded by a helium-burning shell, which is in turn surrounded by a hydrogen-burning shell. The structure becomes layered, like an onion, with different fusion processes occurring at different depths. Stars more massive than the Sun can continue this process, fusing carbon into heavier elements and building up cores of oxygen, neon, magnesium, and beyond. But stars below about 8 solar masses do not have enough gravitational pressure to ignite carbon fusion. For them, the carbon-oxygen core represents the end of the line. No more fusion will occur. The core will simply sit there supported by electron degeneracy pressure, waiting to be revealed. This mass threshold is crucial. It determines whether a star will end as a white dwarf or as something more exotic. Stars above 8 solar masses will continue fusing heavier elements until they develop iron cores and collapse in supernova explosions. Stars below this threshold, the vast majority of stars, will end their nuclear burning lives with carbon-oxygen cores and become white dwarfs. During the later stages of the red giant phase, the star becomes increasingly unstable. The outer layers pulsate, expanding and contracting over periods of months or years. These pulsations drive enhanced mass loss, with each expansion pushing material farther from the star's weakened gravity. Some red giants become what are known as Mira variables, stars that brighten and dim in regular cycles as their outer layers heave in and out. These pulsations are a sign that the star is losing its grip on itself, that the end of the red giant phase is approaching. The mass loss accelerates as the star approaches the end of its red giant life. In the final stages, the star may lose mass at rates thousands of times higher than during the main sequence. This material does not simply vanish. It forms an expanding shell around the star, a cocoon of gas and dust that will eventually become visible as a planetary nebula. The process is gradual, unfolding over tens of thousands of years, but it represents the final shedding of the star's outer layers. Eventually, the envelope becomes so thin that it can no longer sustain the outward pressure needed to maintain the star's bloated size. The outer layers drift away entirely, exposing the hot, dense core beneath. This core, now visible for the first time, is the newborn white dwarf. It is tiny compared to the red giant it once inhabited, but it contains most of the star's remaining mass. The transformation is complete. The star that burned for billions of years has become something new. A glowing ember, a remnant, a quiet end. The process of shedding a star's outer layers creates some of the most beautiful objects in the universe. As the dying star expels its atmosphere, the material forms an expanding shell of gas that glows in the light of the hot core now exposed at the center. These are the planetary nebulae, named not because they have anything to do with planets, but because early astronomers thought their round, fuzzy shapes resembled the disks of distant worlds. Planetary nebulae come in an astonishing variety of shapes. Some are nearly perfect spheres, expanding uniformly in all directions. Others are elongated, stretched into hourglass or butterfly configurations by stellar winds or magnetic fields. Some have multiple shells, created by successive episodes of mass loss. Others show intricate patterns of knots, jets, and streamers that suggest complex interactions between the expelled material and the radiation from the central star. The colors of planetary nebulae are produced by specific atoms glowing at specific wavelengths. Oxygen produces the blue-green hues that dominate many nebulae. Hydrogen contributes shades of red. Nitrogen adds deeper reds and purples. Helium, sulfur, and other elements each add their own tints to the palette. The result is a cosmic art gallery, with each nebula displaying its own unique combination of colors and forms. The central star of a planetary nebula is the newly formed white dwarf. At this stage, it is extraordinarily hot. Surface temperatures can exceed 100,000 degrees, far hotter than the sun's surface temperature of about 5,500 degrees. This intense heat is what ionizes the surrounding gas and causes it to glow. Without the central star's radiation, the nebula would be invisible, just a dark cloud of expanding gas, lost against the backdrop of space. Planetary nebulae are transient phenomena. The expelled gas continues to expand outward at speeds of tens of kilometers per second, gradually thinning and dispersing into the interstellar medium. Within about 20,000 years, the gas becomes too diffuse to glow visibly, and the nebula fades from view. The white dwarf remains, but its shroud disappears, leaving the stellar remnant naked against the darkness. The shapes of planetary nebulae have puzzled astronomers for decades. A single star expelling material uniformly should produce a spherical shell, but many nebulae are far more complex. The leading explanation involves binary companions, other stars, or even large planets orbiting the dying star and shaping the outflow of gas. Magnetic fields may also play a role, channeling material along particular directions. The details vary from nebula to nebula, and each one tells a slightly different story of the death that created it. Some of the most famous nebulae in the sky are planetary nebulae. The Ring Nebula in Lyra appears as a perfect smoke ring suspended among the stars. The Helix Nebula in Aquarius resembles a giant eye staring back at us from deep space. The Cat's Eye Nebula in Draco shows a complex series of concentric shells and jets that hint at a turbulent death. Each of these objects marks the grave of a star not unlike our Sun, a star that burned for billions of years and is now fading into quiet senescence. The material expelled in planetary nebulae does not simply disappear. It carries with it the elements forged during the star's lifetime: carbon, nitrogen, oxygen, and traces of heavier elements produced by slow nuclear processes in the star's interior. These elements mix with the interstellar medium, enriching the gas clouds that will eventually collapse to form new stars and planets. The deaths of stars seed the universe with the raw materials for future generations. This cosmic recycling means that the atoms in your body have passed through multiple stellar generations. The carbon in your cells was forged in the core of a star that died long before the sun was born. The oxygen you breathe was expelled in a planetary nebula billions of years ago. You are made of stardust, not metaphorically, but literally. The white dwarfs scattered across the galaxy are the remains of stars that contributed to this great cycle of creation and destruction. The transition from red giant to white dwarf takes only a few tens of thousands of years, a blink of an eye in stellar terms. The planetary nebula phase is even shorter, lasting only about 20,000 years before the gas disperses. After that, the white dwarf is alone. The shroud has faded. The nuclear fires have gone out. All that remains is a small dense ball of matter glowing with the residual heat of its former life. A newly formed white dwarf is incredibly hot. Surface temperatures can reach 100,000 degrees or more, making these objects some of the hottest stars in the galaxy. But they produce relatively little light because they are so small, only about the size of Earth. A white dwarf might have a surface temperature 20 times that of the sun, but emit only a tiny fraction of the sun's luminosity. The combination of extreme temperature and small size is one of the defining characteristics of these objects. Despite their name, white dwarfs are not always white. The color of a star depends on its surface temperature, and white dwarfs span a wide range of temperatures depending on their age. The youngest, hottest white dwarfs glow blue-white, their surfaces radiating at tens of thousands of degrees. As they cool, they shift through white, yellow, orange, and eventually red. The coolest white dwarfs, if they exist, would glow with a dim red light, barely visible even to sensitive instruments. The first white dwarf ever discovered was Sirius B, the companion to Sirius, the brightest star in the night sky. In 1862, telescope maker Alvin Graham Clark spotted a faint point of light near Sirius while testing a new lens. This companion had been predicted decades earlier based on wobbles in Sirius's motion, but no one expected it to be so dim. When astronomers measured Sirius B's temperature, they found it was hotter than the sun. Yet it produced only a tiny fraction of the sun's light. The only way to reconcile these observations was to conclude that Sirius B was extremely small. It was the first known white dwarf, and it challenged everything astronomers thought they knew about stars. The discovery of white dwarfs posed a puzzle that would take decades to solve. How could an object with the mass of a star fit into a volume the size of a planet? What prevented it from collapsing further under its own gravity? The answer would require entirely new physics, the physics of quantum mechanics, which was just beginning to be developed in the early 20th century. White dwarfs are supported against gravitational collapse by a phenomenon called electron degeneracy pressure. In normal matter, atoms are mostly empty space, with electrons orbiting far from the nucleus. But in a white dwarf, matter is compressed so tightly that the electrons are squeezed into the smallest possible volume allowed by quantum mechanics. The Pauli exclusion principle states that no two electrons can occupy the same quantum state, and this creates an outward pressure that resists further compression. regardless of temperature. This degeneracy pressure is fundamentally different from the thermal pressure that supports normal stars. In the Sun, the outward pressure comes from the heat of nuclear fusion. If the Sun cooled down, it would contract. But in a white dwarf, the degeneracy pressure does not depend on temperature. A white dwarf can cool to absolute zero and still resist gravitational collapse. This is why white dwarfs can exist indefinitely, slowly radiating away their heat without shrinking or changing size. The density inside a white dwarf is almost beyond comprehension. Matter is packed so tightly that a teaspoon of white dwarf material would weigh about 5 tons, as much as an elephant. A sugar cube-sized sample would weigh as much as a car. This extreme density is what allows an entire star's worth of mass to fit into a sphere the size of Earth. At these densities, matter behaves in ways that defy everyday intuition. The electrons in a white dwarf are not bound to individual atoms. Instead, they form a degenerate gas that permeates the entire star. The atomic nuclei, mostly carbon and oxygen, are embedded in this electron sea, arranged in a lattice structure more like a solid than a gas. A white dwarf is, in some sense, a giant crystal floating in space. The mass of a white dwarf determines its size, but the relationship is counterintuitive. More massive white dwarfs are actually smaller than less massive ones. This is because higher mass means stronger gravity, which compresses the degenerate matter more tightly. A white dwarf with half the Sun's mass might be slightly larger than Earth, while one with near the maximum mass would be smaller than Earth. The electrons are squeezed into an ever smaller volume as the mass increases. There is a limit to how massive a white dwarf can be. As mass increases, the electrons are forced to move faster and faster to maintain the degeneracy pressure. At about 1.4 times the mass of the Sun, the electrons would have to move at the speed of light, which is impossible. Beyond this limit, electron degeneracy pressure can't support the star against gravity, and it will collapse into something denser. This maximum mass is called the Chandrasekhar limit, named after the physicist Subramanian Chandrasekhar, who calculated it in 1930 at the age of 19. The Chandrasekhar limit is not just a theoretical curiosity. It has profound implications for the fate of white dwarfs and for our understanding of the universe. White dwarfs that approach this limit can explode as type 1, a supernovae, some of the most powerful explosions in the cosmos. These explosions have been used to measure the expansion of the universe and led to the discovery that cosmic expansion is accelerating. A young physicist's calculation about the maximum mass of stellar remnants helped revolutionize our understanding of cosmology. Most white dwarfs have masses between about half and slightly less than the Sun's mass. This is because stars shed most of their mass during the red giant phase. A star that begins with several times the Sun's mass may end up with a white dwarf remnant of less than 1 solar mass. The mass of the white dwarf depends on the mass of the original star, but the relationship is not linear. More massive progenitors produce more massive white dwarfs, but only up to a point. The composition of a white dwarf depends on the mass of the star that created it. Most white dwarfs are made primarily of carbon and oxygen, the products of helium fusion, but white dwarfs from the lowest mass stars may be made almost entirely of helium, because these stars never got hot enough to fuse helium into heavier elements. At the other end of the spectrum, white dwarfs from stars just below the supernova threshold may contain significant amounts of oxygen neon, and magnesium. The surface composition of a white dwarf can differ from its interior. Over time, heavier elements sink toward the center, while lighter elements float to the top. Most white dwarfs have surfaces dominated by hydrogen, even though hydrogen makes up only a thin outer layer. Others have surfaces of nearly pure helium, having lost their hydrogen envelopes or mixed them into deeper layers. The surface composition affects the white dwarf's spectrum and provides clues about its history. White dwarfs are born spinning rapidly, inheriting the angular momentum of the stars that created them. But over time, they slow down. Without any source of energy to drive winds or jets, white dwarfs simply rotate in the darkness, their spin rates gradually decreasing over billions of years. Some young white dwarfs complete a rotation in minutes. The oldest may take hours or even days. The magnetic fields of white dwarfs vary enormously. Some have magnetic fields comparable to Earth's, barely detectable and dynamically unimportant. Others have fields millions or even billions of times stronger, powerful enough to affect the structure of atoms at their surfaces. These highly magnetic white dwarfs may have acquired their fields from the stars that created them, or generated them during the collapse from red giant to white dwarf. The surface gravity of a white dwarf is about 100,000 times stronger than Earth's gravity. An object that weighs 1 kilogram on Earth would weigh 100,000 kilograms on the surface of a white dwarf. This intense gravity affects everything about the star, from the way light bends near its surface to the way atoms behave in its atmosphere. If you could somehow stand on a white dwarf, you would be instantly crushed into a thin film of matter. Despite their exotic properties, white dwarfs are remarkably stable. They do not collapse. They do not expand. They do not undergo dramatic changes. They simply exist, slowly radiating their heat into the void. A white dwarf today will look almost identical a billion years from now, except that it will be slightly cooler and slightly dimmer. This stability makes white dwarfs some of the most patient objects in the universe. The cooling of a white dwarf is a simple process governed by basic physics. The star has a finite amount of thermal energy stored in its interior, and it radiates this energy away through its surface. As the interior cools, the surface cools as well, and the rate of energy loss decreases. This means that white dwarfs cool more slowly as they age. A hot young white dwarf loses heat rapidly, while a cool old one loses heat almost imperceptibly. The cooling curve of a white dwarf can be calculated with remarkable precision. By measuring the temperature and luminosity of a white dwarf, astronomers can estimate how long ago it formed. This makes white dwarfs excellent cosmic clocks, capable of dating events that occurred billions of years ago. The oldest white dwarfs in the Milky Way provide a lower limit on the age of the galaxy itself. The interior of a cooling white dwarf undergoes a phase transition that affects its cooling rate. At a certain temperature, the carbon and oxygen nuclei in the white dwarf's core begin to crystallize, forming a solid lattice structure. This crystallization releases latent heat, energy that was stored in the disordered motion of the nuclei and is released when they lock into place. The release of this energy temporarily slows the cooling of the white dwarf. The crystallization of white dwarfs was predicted theoretically decades ago, but observational evidence has only recently become available. Studies of large populations of white dwarfs have found a pileup of stars at certain temperatures, more than would be expected from simple cooling models. This pileup corresponds to the temperature at which crystallization occurs, confirming that white dwarfs are indeed freezing solid from the inside out. A crystallizing white dwarf is essentially becoming a giant diamond. Carbon and oxygen nuclei arranged in a crystalline lattice form a structure similar to diamond, though the pressures and compositions are different from terrestrial diamonds. Some white dwarfs, particularly those with higher carbon content, may contain cores of nearly pure crystallized carbon. Diamonds, the size of Earth, drifting through the galaxy. The idea of diamond stars captured the public imagination when it was first proposed, and it remains one of the most poetic facts about white dwarfs. Somewhere in the darkness, the remains of stars that burned for billions of years are slowly crystallizing into gems beyond anything found on Earth. They will never be mined, never be seen, never be touched, but they exist, silent and perfect, throughout the galaxy. The crystallization of white dwarfs also affects their internal structure. As the core solidifies, it becomes denser than the surrounding liquid, and heavier elements sink toward the center. This process of gravitational settling releases additional energy and can significantly extend the cooling time of massive white dwarfs. The interiors of these ancient stars are still evolving, even though their nuclear fires went out billions of years ago. The atmospheres of white dwarfs are surprisingly thin and remarkably pure. Because surface gravity is so strong, heavier elements sink rapidly toward the interior, leaving only the lightest elements floating at the top. Most white dwarfs have atmospheres of nearly pure hydrogen or pure helium, with traces of heavier elements present only if they are being actively deposited by infalling material. Some white dwarfs show spectral evidence of heavy elements like calcium, magnesium, iron, and even water in their atmospheres. These elements should sink below the visible surface within days, so their presence indicates ongoing accretion, material falling onto the white dwarf from an external source. In many cases, this material appears to come from asteroids, comets, or planetary debris that wandered too close to the white dwarf and was torn apart by its gravity. The pollution of white dwarf atmospheres by infalling debris provides a unique window into the composition of extrasolar planetary systems. By analyzing the elements in a polluted white dwarf's atmosphere, astronomers can determine what the accreted objects were made of, effectively measuring the composition of asteroids or planetary fragments in distant star systems. This technique has revealed that rocky material around other stars is broadly similar to rocky material in our own solar system. Some white dwarfs are surrounded by disks of debris, visible as excess infrared radiation emanating from dust, heated by the star's light. These disks are the shattered remains of asteroids or minor planets that ventured too close and were ripped apart by tidal forces. The debris gradually spirals inward, eventually falling onto the white dwarf's surface. These dusty disks are like crime scenes, marking the destruction of planetary bodies billions of years after their formation. A small fraction of white dwarfs are not alone. Despite the violence of their formation, some white dwarfs retain planetary companions, worlds that survived the death of their star, though not unscathed. Gas giants that orbited at safe distances may survive the red giant phase and continue orbiting the white dwarf. Rocky planets in inner orbits are less fortunate. Most are engulfed or evaporated during the star's expansion. Detecting planets around white dwarfs is challenging because the stars are so faint, but several candidates have been found. In 2020, astronomers discovered strong evidence for a giant planet orbiting a white dwarf, detected by observing the subtle gravitational tug it exerted on its host. Other white dwarfs show evidence of planets that are actively being destroyed, bodies that ventured close enough to be torn apart by tidal forces and are now raining down onto the stellar surface. The fate of the Earth when the Sun becomes a white dwarf is uncertain. Models suggest that Earth may be engulfed during the Sun's red giant phase, vaporized by the expanding stellar envelope. Even if it survives, it will be a frozen, lifeless world orbiting a dim and cooling ember. The oceans will have boiled away long before, during the Sun's main sequence brightening. The Earth that remains, if it remains, will bear no resemblance to the world we know. Other planets in our solar system have better prospects. Mars may survive the red giant phase, though it will be scorched by the expanded Sun. Jupiter and Saturn will certainly survive, though they may migrate inward as the Sun loses mass. The outer solar system will persist, a frozen collection of worlds orbiting a white dwarf that was once a yellow star called the Sun. In some sense, the solar system will outlive the star that gave it its name. White dwarfs do not exist in isolation. Many are members of binary systems, orbiting other stars or other white dwarfs. Some formed in binaries and have remained paired throughout their evolution. Others were captured gravitationally or formed from the merger of closer pairs. The dynamics of binary white dwarfs can lead to some of the most dramatic events in the universe. When two white dwarfs orbit very close to each other, they gradually spiral inward due to the emission of gravitational waves. This process is extremely slow, but over billions of years, it can bring the two stars close enough to merge. What happens next depends on the combined mass. If the total exceeds the Chandrasekhar limit, the merger may trigger a thermonuclear explosion, a type 1 a supernova. If the combined mass is below the limit, the merger may produce a single, more massive white dwarf. Gravitational waves from binary white dwarfs are a form of cosmic radiation that we are only beginning to detect. These waves are ripples in the fabric of space-time, produced whenever massive objects accelerate. Current gravitational wave detectors on Earth are sensitive to the waves produced by merging black holes and neutron stars, but binary white dwarfs produce waves at lower frequencies that require space-based detectors. Future missions like LISA will open this new window on the universe. Some white dwarfs in binary systems are close enough to steal matter from their companions. If the companion is a normal star, material can flow from its outer layers onto the white dwarf, accumulating on the surface. This process is called mass transfer, and it can have dramatic consequences. The transferred material is typically rich in hydrogen, which piles up on the white dwarf's surface until it reaches a critical depth. At this point, the pressure and temperature at the base of the accumulated layer become high enough to ignite nuclear fusion. The hydrogen explodes in a brilliant flash called a nova, a thermonuclear runaway on the surface of a white dwarf. A nova is not the same as a supernova. In a nova, only the thin layer of accumulated hydrogen explodes. The white dwarf itself survives. After the explosion, the process begins again. More matter accumulates, the pressure builds, and eventually another nova erupts. Some white dwarfs have experienced dozens of recorded novae, flashing into visibility every few decades as their stolen fuel ignites. During a nova, a white dwarf can brighten by a factor of 100,000 or more. becoming visible across interstellar distances. Ancient astronomers recorded novae as new stars, appearing suddenly in the sky, sometimes visible for weeks or months before fading back into obscurity. The word nova itself comes from the Latin for new, reflecting the surprise of early observers who did not understand what they were seeing. The material ejected in a nova enriches the interstellar medium with elements synthesized during the explosion. Novae produce significant quantities of nitrogen, oxygen, neon, and other elements that contribute to the chemical evolution of galaxies. While less dramatic than supernovae, novae are more common and may play an important role in seeding the universe with heavy elements. If a white dwarf in a binary system accumulates mass quickly enough, it may approach the Chandrasekhar limit. When the mass exceeds this critical threshold, electron degeneracy pressure can no longer support the star, and something dramatic happens. In some cases, the core begins to fuse carbon in a runaway thermonuclear reaction. Unlike the helium flash in a normal star, this carbon fusion cannot be quenched. The entire white dwarf is incinerated in a fraction of a second. This is a Type 1a supernova, one of the most powerful explosions in the universe. The white dwarf is completely destroyed, its matter flung into space at thousands of kilometers per second. The explosion releases as much energy as the sun will produce over its entire 10 billion year lifetime. And for a few weeks, the supernova can outshine its entire host galaxy. Type 1a supernova are remarkably consistent in their peak brightness, which makes them valuable tools for measuring cosmic distances. By comparing the apparent brightness of a Type 1a supernova in a distant galaxy to its known intrinsic brightness, astronomers can calculate how far away that galaxy is. This technique has been used to map the expansion of the universe and led to the discovery that expansion is accelerating, one of the most surprising findings in modern cosmology. Not all white dwarfs that exceed the Chandrasekhar limit explode as supernovae. Some may collapse directly into neutron stars, a fate usually reserved for more massive stellar cores. The details depend on the composition of the white dwarf and the rate at which mass was added. The physics of these extreme events is still being explored. The frequency of Type 1, a supernovae in a galaxy, depends on the population of white dwarfs and their binary companions. In the Milky Way, a Type 1, a supernova, occurs roughly once every few hundred years. The last one visible to the naked eye was Tycho supernova in 1572, observed by the astronomer Tycho Brahe, and contributing to the revolution in astronomical thinking that followed. White dwarfs have been cooling in the Milky Way since the first generations of stars began to die, billions of years ago. The oldest white dwarfs in the galaxy are so ancient and so cool that they are nearly invisible. Faint red embers, barely distinguishable from the background noise of the universe. These ancient remnants serve as fossils of the early galaxy, preserving information about conditions that existed long before the sun was born. By studying populations of white dwarfs, astronomers can reconstruct the history of star formation in the Milky Way. The distribution of white dwarf temperatures and luminosities reflects when stars formed and died over the galaxy's lifetime. Cool white dwarfs indicate ancient stellar populations, while hot ones mark recent deaths. This technique of white dwarf cosmochronology provides an independent check on other methods of dating the galaxy. The oldest white dwarfs in the Milky Way are estimated to be around 11 billion years old. This places a lower limit on the age of the galaxy's disk. It must be at least as old as its oldest stellar remnants. The universe itself is about 13.8 billion years old, so these ancient white dwarfs formed when the cosmos was only a few billion years old. Some white dwarfs move through the galaxy at unusually high velocities, suggesting they were ejected from binary systems or kicked by supernova explosions. These hypervelocity white dwarfs travel fast enough to escape the Milky Way entirely, destined to wander intergalactic space forever. Their journeys began in the galaxy, but they will end in the void between galaxies, cooling in perfect isolation. The space between stars is not entirely empty, and white dwarfs occasionally pass through denser regions of interstellar gas and dust. When this happens, the white dwarf's gravity can attract material from the surrounding medium, and a faint accretion glow may result. These interactions are rare and subtle, but they demonstrate that white dwarfs, even in their quiet senescence, continue to interact with the universe around them. In globular clusters, ancient spherical collections of hundreds of thousands of stars, white dwarfs make up a significant fraction of the stellar population. These clusters are among the oldest structures in the galaxy, and many of their original stars have long since died. The white dwarfs that remain are cooling slowly, their light contributing to the faint background glow of the cluster. Globular cluster white dwarfs provide excellent laboratories for studying stellar evolution. Because all the stars in a cluster formed at roughly the same time, their white dwarfs represent a single generation of stellar death. By studying the distribution of white dwarf properties in a cluster, astronomers can test models of stellar evolution and cooling with remarkable precision. Some globular clusters contain white dwarfs that have been rejuvenated through interactions with other stars. In the dense cores of these clusters, stars pass close to each other frequently, and occasionally a white dwarf can capture mass from a passing companion or merge with another object. These rejuvenated white dwarfs may appear younger than they actually are, complicating efforts to date the cluster. The density of stars in globular cluster cores can lead to exotic systems involving white dwarfs. Binary white dwarfs may be common, as gravitational encounters nudge pairs into closer orbits. Some white dwarfs may orbit pulsars, neutron stars, or even black holes. These mixed pairs produce unique observational signatures and provide laboratories for testing theories of gravity and dense matter. Beyond globular clusters, white dwarfs are found throughout the Milky Way's disk and halo. They orbit the galactic center along with other stars, tracing the same gravitational paths, but emitting only a tiny fraction of the light. The total mass of white dwarfs in the Milky Way is estimated to be comparable to the mass of all visible stars, making them a significant but hidden component of the galaxy. Most white dwarfs are close enough that they could be detected with sufficiently sensitive instruments, but their faintness makes comprehensive surveys challenging. Current catalogs contain hundreds of thousands of known white dwarfs, but this represents only a small fraction of the total population. Future telescopes and surveys will continue to expand our census, revealing ever fainter and older remnants. The nearest known white dwarf to Earth is Sirius B, only 8.6 light-years away. Despite its proximity, it is invisible to the naked eye, overwhelmed by the brilliance of its companion, Sirius A. Through a telescope, it appears as a faint point of light, a tiny ember beside a blazing diamond. Few objects illustrate the difference between living and dying stars so dramatically. Another nearby white dwarf, Procyon b, orbits the star Procyon about 11.5 light-years from Earth. Like Sirius B, it was detected by its gravitational influence before it was seen directly. Procyon b is slightly cooler and less massive than Sirius B, reflecting differences in the stars that created them. Van Manen star, about 14.1 light-years away, is the closest solitary white dwarf to Earth. Unlike Sirius B and Procyon b, it does not have a bright companion to overwhelm its light. It is visible through modest telescopes as a faint star in the constellation Pisces, a lonely ember drifting through the local neighborhood. These nearby white dwarfs provide opportunities for detailed study. Their proximity makes them easier to observe at high resolution, revealing details of their atmospheres and magnetic fields. They serve as benchmarks for understanding more distant objects, and their proper motions across the sky are easily measured, allowing precise calculations of their velocities and orbits. The population of white dwarfs in the solar neighborhood is diverse. Some are hot and young, recently formed from the deaths of stars that lived fast and died early. Others are cool and ancient, the remains of stars that burned for billions of years before releasing their outer layers. Together, they represent a cross-section of stellar death across cosmic time. The distribution of white dwarfs in the galaxy traces the history of star formation. Regions that formed many stars long ago now contain many white dwarfs. Regions of recent star formation are dominated by living stars, their dying phases still ahead. By mapping the white dwarf population, astronomers create a fossil record of the galaxy's stellar history. White dwarfs are found in all types of galaxies, not just the Milky Way. Spiral galaxies, elliptical galaxies, and dwarf galaxies all contain populations of these cooling remnants. The oldest elliptical galaxies, which ceased forming stars billions of years ago, should be particularly rich in white dwarfs. Their stellar populations have had ample time to evolve through their life cycles. In distant galaxies, individual white dwarfs are too faint to observe directly, but their collective light contributes to the galaxy's overall spectrum, and certain features can reveal the presence of white dwarf populations. Theoretical models predict how many white dwarfs should exist in galaxies of different types and ages, providing tests of our understanding of stellar evolution. The total number of white dwarfs in the observable universe is staggering. With hundreds of billions of galaxies, each containing billions of stars and their remnants, the count reaches into the quintillions or higher. Most of these white dwarfs will never be observed individually, but they exist, silent, cooling, patient, scattered throughout the cosmos like embers from an unimaginably vast fire. The cooling of a white dwarf is one of the simplest and most predictable processes in astrophysics. Unlike living stars, which burn fuel and undergo complex internal changes, a white dwarf simply radiates heat. It has no energy source, no nuclear reactions, no way to replenish what it loses. It is like a stone pulled from a fire, glowing brightly at first, but destined to fade. The mathematics of this cooling are well understood, and they reveal timescales that stretch far beyond anything in human experience. A newly formed white dwarf begins its cooling journey at temperatures exceeding 100,000 degrees. At this stage, it radiates energy furiously, its surface glowing with intense ultraviolet and blue-white light. But even at these extreme temperatures, The total luminosity is modest because the surface area is so small. A white dwarf the size of Earth, no matter how hot, cannot compete with a star the size of the Sun in terms of raw energy output. As the white dwarf cools, its luminosity drops. The relationship between temperature and luminosity follows a steep power law. A small decrease in temperature leads to a large decrease in brightness. A white dwarf that has cooled from 100,000 degrees to 50,000 degrees has lost far more than half its luminosity. This rapid dimming continues for millions of years, with the white dwarf fading from a brilliant blue-white ember to a more modest yellow glow. The rate of cooling depends on the white dwarf's mass, composition, and atmospheric structure. More massive white dwarfs have smaller surface areas relative to their stored heat, so they cool more slowly. White dwarfs with hydrogen-rich atmospheres cool differently than those with helium-rich atmospheres because the two gases have different opacities and conduct heat differently. These variations create a range of cooling behaviors that astronomers can use to infer the properties of individual white dwarfs. After about 100 million years, a typical white dwarf has cooled to a surface temperature of around 10,000 degrees, still hot by everyday standards, but cool enough to glow with a yellowish white light. At this stage, the white dwarf has faded to less than 1% of its initial luminosity. It is still visible through telescopes, but it is no longer among the brighter objects in its stellar neighborhood. The cooling continues, though at an ever slower pace. As the white dwarf's temperature drops, the rate of energy loss decreases as well. A white dwarf at 10,000 degrees loses energy much more slowly than one at 50,000 degrees. This means that the later stages of cooling take far longer than the early stages. The first billion years of a white dwarf's life see dramatic changes. The next billion years see far more subtle ones. By the time a white dwarf reaches a surface temperature of around 5,000 degrees, comparable to the surface of the Sun, it has been cooling for several billion years. At this stage, it glows with a warm orange-red light, barely visible against the background of brighter stars. Its luminosity is a tiny fraction of what it was at birth, and it continues to fade. The oldest white dwarfs in the Milky Way have surface temperatures of around 4,000 degrees or less. These ancient remnants have been cooling for 10 billion years or more, since before the Sun existed. They are among the faintest objects in the galaxy, visible only to the most sensitive instruments. Their dim red glow is the last whisper of stars that burned brightly when the universe was young. Finding these ancient white dwarfs is a challenge. They are faint, they move slowly across the sky, and they can easily be confused with other dim red objects, like cool red dwarfs or distant background stars. But they are invaluable for understanding the history of the galaxy. Each ancient white dwarf is a fossil, a remnant of a star that formed and died in the distant past, carrying information about conditions that no longer exist. The cooling of white dwarfs is so predictable that astronomers use them as cosmic clocks. By measuring the temperature and luminosity of a white dwarf, they can calculate how long it has been cooling. This technique, called white dwarf cosmochronology, provides independent estimates of the ages of stellar populations, star clusters, and even the galaxy itself. White dwarf cosmochronology works best for populations of white dwarfs rather than individuals. A single white dwarf might have an uncertain mass or composition, leading to errors in the age estimate, But a large population of white dwarfs will show a characteristic distribution of temperatures and luminosities that reflects the history of star formation and death. By modeling this distribution, astronomers can reconstruct when the stars in a population formed. The coolest white dwarfs in the Milky Way's disk set a lower limit on the age of the disk. If the disk were younger, these white dwarfs would not have had time to cool to such low temperatures. Current estimates suggest that the oldest disk white dwarfs are about 10 billion years old, which means the disk itself must be at least that ancient. This is consistent with other age estimates for the Milky Way. White dwarfs in the galactic halo are even older. The halo is a roughly spherical region surrounding the disk, containing ancient stars that formed in the earliest epochs of the galaxy's history. White dwarfs in the halo have been cooling for 11 billion years or more, making them some of the oldest objects in the Milky Way. Their faint glow is a direct link to the galaxy's infancy. The cooling of white dwarfs does not continue indefinitely at a steady pace. At certain temperatures, physical changes occur in the white dwarf's interior that affect the cooling rate. The most significant of these is crystallization, the transition from a liquid-like state to a solid, crystalline lattice. This phase change releases latent heat, temporarily slowing the cooling process. Crystallization begins in the core of a white dwarf, when the interior temperature drops to around a few million degrees. At these temperatures, the thermal energy of the carbon and oxygen nuclei is no longer sufficient to keep them in a disordered, liquid-like state. The nuclei settle into a regular lattice, minimizing their energy and releasing the excess as heat. This heat must be radiated away before cooling can continue. The crystallization process takes time, hundreds of millions to billions of years, depending on the white dwarf's mass. During this period, the white dwarf's cooling is significantly delayed. Observations of large populations of white dwarfs have confirmed this effect, showing a pileup of stars at the temperatures where crystallization is expected to occur. As crystallization proceeds, the solid core grows outward from the center. The boundary between solid and liquid advances through the white dwarf's interior like a freezing front, gradually converting the entire star into a crystalline solid. The outer layers remain liquid longest, insulated by the solid core beneath. The crystals that form in a white dwarf's core are not like ordinary crystals on Earth. They are made of bare atomic nuclei, carbon and oxygen nuclei stripped of their electrons, arranged in a lattice, and embedded in a sea of degenerate electrons. The structure is more like a metal than like ice or diamond, though the analogy to diamond is often made because both involve carbon atoms in a crystalline arrangement. Recent research has revealed an additional complication in the crystallization process. As the crystal forms, heavier elements like oxygen tend to sink toward the center, while lighter elements like carbon float upward. This gravitational settling releases additional energy, further delaying the cooling of the white dwarf. The effect is most pronounced in massive white dwarfs, where gravity is strongest. The settling of heavy elements during crystallization has implications for white dwarf ages. White dwarfs that have undergone significant settling will appear younger than they actually are, because the extra energy release has kept them warmer for longer. Correcting for this effect is important for accurate white dwarf cosmochronology. Some white dwarfs show evidence of unusual crystallization behavior. Highly magnetic white dwarfs, for example, may crystallize differently than non-magnetic ones because the magnetic field affects the motion of charged particles in the interior. White dwarfs with unusual compositions may also show different crystallization patterns. The end state of white dwarf crystallization is a star that is almost entirely solid. The degenerate electrons continue to flow freely, conducting heat from the interior to the surface, but the nuclei are locked in place, forming a rigid lattice that will persist for timescales far exceeding the current age of the universe. A fully crystallized white dwarf is sometimes described as a cosmic diamond, though this is somewhat poetic. The carbon nuclei in the crystal are arranged differently than the carbon atoms in a terrestrial diamond, and the presence of oxygen and other elements further complicates the comparison. But the image captures something true. These are objects of remarkable structure and durability, formed over billions of years and destined to persist for trillions more. The thermal energy stored in a white dwarf's crystalline core will eventually be exhausted. As the white dwarf continues to radiate heat, its temperature drops ever lower. After tens of billions of years, the surface temperature may fall below 1,000 degrees, cooler than a candle flame. The white dwarf will glow with a dim infrared light, invisible to human eyes, but still detectable to infrared telescopes. The universe is not yet old enough for any white dwarf to have cooled this far. The oldest white dwarfs, at around 11 billion years old, still have surface temperatures of several thousand degrees, but given enough time, they will continue to cool, eventually reaching temperatures that are barely above absolute zero. The theoretical end state of a white dwarf is called a black dwarf, a completely cooled stellar remnant, emitting no light or heat. A black dwarf would be a dark, cold ball of crystallized carbon and oxygen, invisible against the backdrop of space. It would have the mass of a star, but the temperature of interstellar space, a frozen monument to a star that burned billions of years ago. No black dwarfs exist yet. The time required for a white dwarf to cool to this state is estimated at trillions of years, far longer than the current age of the universe. The first black dwarfs will not form for an almost unimaginable span of cosmic time, but eventually, if the universe continues to expand and cool, all white dwarfs will reach this final state. The concept of black dwarfs highlights the extreme patience of cosmic processes. Human civilization spans mere thousands of years. The age of the universe is measured in billions of years, but the cooling of white dwarfs into black dwarfs requires trillions of years, a timescale so vast that it dwarfs even the age of the cosmos. On such scales, the entire history of the universe to date is merely a prologue. In the far future, when the last stars have burned out and the last white dwarfs have faded, black dwarfs will be among the few remaining objects in a dark and empty universe. They will drift through the void, carrying within them the frozen remains of the nuclear fires that once lit the cosmos. No light will shine, no heat will radiate, only mass and gravity will remain, silent witnesses to an age of brilliance long past. The fate of black dwarfs in the extreme far future is even more exotic. On timescales of 10 to the power of 65 years and beyond, even the protons and neutrons that make up atomic nuclei may decay, if certain theories of particle physics are correct. If proton decay occurs, black dwarfs will slowly evaporate, their matter dissolving into radiation and lighter particles. The end result would be complete. The black dwarf would simply cease to exist. If protons do not decay, black dwarfs may persist indefinitely, drifting through an ever-emptying universe. Occasionally, two black dwarfs might collide in the darkness, releasing a burst of energy from the impact. More rarely, quantum tunneling effects might cause black dwarfs to undergo fusion or collapse, though such events would take timescales so long that they are difficult to comprehend. The study of these far future scenarios is called physical eschatology, the physics of ultimate endings. It is a speculative field, necessarily so, because the timescales involved are so far beyond observation. But it is grounded in known physics, and it provides a framework for understanding what the universe might become in the unimaginably distant future. White dwarfs occupy a central place in this cosmic narrative. They are the most common stellar remnants, and they represent the fate of most stars in the universe. When the era of star formation ends, when the last hydrogen has been fused, and the last supernovae have flared, white dwarfs will be the dominant remnants. Their slow cooling is the final chapter in the story of stellar evolution. The cooling timescales of white dwarfs also have implications for the search for extraterrestrial life. A white dwarf that retains planetary companions could, in principle, provide a stable source of heat for billions of years, far longer than the main sequence lifetime of a sun-like star. If life could adapt to the changing conditions as a star evolves from main sequence to red giant to white dwarf, it might persist in a white dwarf system for an extraordinarily long time. The habitable zone around a white dwarf is very different from the habitable zone around a main sequence star. Because white dwarfs are so small and dim, their habitable zones are extremely close. A planet would need to orbit at a distance of only a few % of Earth's orbital distance to receive comparable warmth. At such close distances, the planet would be tidally locked, with one hemisphere perpetually facing the star and the other in eternal darkness. Despite these challenges, some researchers have speculated that white dwarf systems could support life. A planet in the habitable zone of a white dwarf would receive steady illumination for billions of years, longer than the sun has existed. If life could establish itself during or after the red giant phase, it would have an extraordinarily long window of opportunity to evolve and thrive. Detecting planets in the habitable zones of white dwarfs is difficult, but not impossible. Transit searches, which look for the dimming of a star's light as a planet passes in front of it, are particularly sensitive for white dwarfs because the small size of the star means that even a small planet produces a significant dimming. Several ongoing surveys are searching for such transits, hoping to find worlds orbiting these ancient stellar embers. The possibility of life around white dwarfs adds another dimension to the search for habitable worlds beyond our solar system. Most attention has focused on main sequence stars, but white dwarfs offer an alternative. One where stability is measured in billions rather than millions of years. In a universe where most stars will eventually become white dwarfs, this alternative pathway could be cosmically significant. White dwarfs also play important roles in our understanding of fundamental physics. Because they contain matter at extreme densities, they serve as natural laboratories for studying the behavior of degenerate matter. The properties of white dwarfs, their masses, radii, and cooling curves, provide tests of quantum mechanics and statistical physics under conditions impossible to replicate on Earth. The mass-radius relationship of white dwarfs is one of the cleanest predictions of quantum mechanics. Electron degeneracy pressure, which supports white dwarfs against gravity, arises from the Pauli exclusion principle, the rule that no two electrons can occupy the same quantum state. This fundamental principle of quantum mechanics leads directly to the prediction that more massive white dwarfs should be smaller, a prediction that has been confirmed by observations. Measurements of white dwarf masses and radii provide tests of our understanding of dense matter physics. The most precise measurements come from white dwarfs in binary systems, where gravitational interactions allow the masses to be determined independently. These measurements consistently agree with theoretical predictions, confirming that our understanding of degenerate matter is correct. White dwarfs also provide opportunities to test theories of gravity. In strong gravitational fields, Einstein's general theory of relativity predicts subtle effects that differ from Newtonian gravity. White dwarfs, with their intense surface gravity, produce measurable relativistic effects. Light emitted from the surface of a white dwarf is redshifted by the gravitational field. Photons lose energy as they climb out of the gravitational well. This gravitational redshift has been measured for several white dwarfs and agrees with the predictions of general relativity. The gravitational bending of light near white dwarfs is another relativistic effect that can be observed. When a white dwarf passes in front of a more distant star, its gravity bends the light from the background star, causing the star to appear slightly displaced. This effect, called gravitational lensing, has been used to measure the masses of isolated white dwarfs that are not in binary systems. The intense magnetic fields of some white dwarfs provide additional laboratories for fundamental physics. In the strongest magnetic fields, exceeding 1 billion times Earth's magnetic field, the structure of atoms is dramatically altered. Electrons are confined to move along magnetic field lines, and the energy levels of atoms shift in ways that produce unfamiliar spectral features. Studying these effects tests our understanding of quantum mechanics in extreme conditions. Some white dwarfs pulsate, rhythmically expanding and contracting over periods of minutes. These pulsations are driven by instabilities in the star's outer layers, where the ionization state of atoms changes with temperature. The pulsations cause the white dwarf's brightness to vary slightly, and by studying these variations, astronomers can probe the internal structure of the star. White dwarf pulsations are a form of asteroseismology, the study of stellar interiors through oscillations. Just as seismologists use earthquakes to study Earth's interior, astronomers use stellar pulsations to study what lies beneath a star's surface. The frequencies of the pulsations depend on the white dwarf's mass, composition, and internal temperature profile, providing information that would otherwise be inaccessible. The pulsating white dwarfs are classified into several groups based on their temperatures and atmospheric compositions. The hottest pulsating white dwarfs with helium-rich atmospheres oscillate with periods of a few hundred seconds. Cooler hydrogen atmosphere pulsators have longer periods, up to about 1,000 seconds. The coolest pulsators, still being discovered, may have even longer periods. The study of white dwarf pulsations has revealed that these stars have layered structures, with thin outer envelopes of hydrogen or helium surrounding carbon-oxygen cores. The pulsations are sensitive to the thicknesses of these layers, allowing astronomers to measure quantities that cannot be observed directly. This information helps constrain models of stellar evolution and mass loss. Some white dwarf pulsation periods change over time, providing a direct measurement of the cooling rate. As a white dwarf cools, its internal structure changes slightly, and the pulsation periods shift accordingly. By monitoring these changes over years or decades, astronomers can measure how quickly the white dwarf is losing energy, a direct window into the physics of white dwarf cooling. The most precise pulsation measurements have revealed unexpected complexity in white dwarf interiors. Some white dwarfs show pulsation modes that suggest the presence of internal composition gradients or crystallizing cores. Others show evidence of rotation or magnetic fields affecting the oscillations. Each new discovery adds to our understanding of these deceptively simple-seeming objects. White dwarfs in binary systems provide some of the most dramatic phenomena in stellar astrophysics. We have already discussed novae and Type 1 supernovae, but there are other exotic systems involving white dwarfs that deserve attention. These systems showcase the diversity of outcomes possible when white dwarfs interact with companions. Cataclysmic variables are binary systems in which a white dwarf accretes matter from a close companion star. The matter does not fall directly onto the white dwarf. Instead, it spirals inward through an accretion disk, heated by friction and gravitational energy. These disks can outshine the white dwarf itself, producing flickering, variable light that has fascinated astronomers for over a century. The accretion disks in cataclysmic variables are turbulent, dynamic structures. Matter spirals inward through the disk, occasionally piling up and then releasing in outbursts. These outbursts, called dwarf novae, cause the system to brighten by several magnitudes over periods of days to weeks. Unlike classical novae, which involve nuclear explosions on the white dwarf's surface, dwarf novae are powered purely by gravitational energy released in the accretion disk. Some cataclysmic variables contain highly magnetic white dwarfs. In these systems, the magnetic field is strong enough to disrupt the inner accretion disk, channeling matter along magnetic field lines onto the white dwarf's magnetic poles. The result is a system called a polar or AM Hercules star, named after the prototype system. Polars produce X-rays and show polarized optical light, signatures of matter being funneled by intense magnetic fields. Intermediate polars are systems where the magnetic field is strong, but not strong enough to completely disrupt the accretion disk. In these systems, matter flows through a partial disk before being captured by the magnetic field and directed onto the poles. The result is a complex interplay between disk accretion and magnetically channeled accretion, producing a rich variety of observational signatures. The evolution of cataclysmic variables is driven by angular momentum loss. As the binary system loses angular momentum through magnetic braking, gravitational wave emission, or other processes, the two stars spiral closer together. This increases the rate of mass transfer, which in turn affects the evolution of both the white dwarf and its companion. Over billions of years, these systems evolve through various stages, eventually reaching a minimum orbital period before the companion star is completely consumed or the system detaches. Some of the closest binary systems known contain two white dwarfs orbiting each other. These double white dwarf binaries are the end products of binary stellar evolution, in which both stars have passed through their life cycles and shed their envelopes. The orbital periods of these systems can be remarkably short. Some complete an orbit in less than an hour. Double white dwarf binaries are important sources of gravitational waves. As the two white dwarfs orbit each other, they emit gravitational radiation, losing energy and spiraling closer together. The frequency of the gravitational waves depends on the orbital period, and for the closest systems, These waves fall in the frequency range that future space-based detectors will observe. The eventual fate of a close double white dwarf binary is merger. As the stars spiral together, they will eventually come close enough that tidal forces begin to distort them. The less massive white dwarf will be disrupted first, its matter spreading into a disk around the more massive companion. What happens next depends on the total mass and the rate of accretion. If the total mass of the merging white dwarfs exceeds the Chandrasekhar limit, the merger may trigger a Type 1 supernova. This is one of the proposed channels for producing these standardizable explosions. The details of how the merger proceeds and whether it leads to an explosion or collapse are still being studied, both theoretically and through observations of merger candidates. If the total mass is below the Chandrasekhar limit, the merger may produce a single, more massive white dwarf. This remnant would spin rapidly and might have unusual surface composition from the mixing of the two original stars. Some unusual white dwarfs observed today may be the products of ancient mergers. An alternative outcome of white dwarf mergers is the formation of a neutron star. If the merger product is massive enough and the matter is compressed sufficiently, electron degeneracy pressure may fail and the object may collapse to neutron star densities. This would be accompanied by the release of enormous amounts of energy, though not in the form of a typical supernova. The merger of two white dwarfs can also produce transient events that are less energetic than supernova, but still spectacular. These include objects called subluminous supernovae, or type IAX supernovae, which are fainter and evolve differently than classical type 1a events. The diversity of white dwarf merger outcomes reflects the complexity of these events. White dwarfs have been found in some surprising locations. In 2011, astronomers discovered a planet-sized object orbiting a pulsar, a rapidly rotating neutron star, at very close range. The object's density was consistent with a white dwarf that had been stripped of most of its mass by interactions with the pulsar. This strange system, called a Black Widow system, showcases the extreme environments in which white dwarfs can exist. Some white dwarfs have been found in triple or even quadruple star systems. These hierarchical systems contain white dwarfs orbiting with other stars at various distances, creating complex gravitational dynamics. The presence of a third body can influence the evolution of a close binary, potentially triggering mass transfer or mergers that would not occur in isolated binaries. The search for white dwarfs in star clusters has revealed much about stellar evolution. Open clusters, which are loose associations of stars born together, contain white dwarfs whose masses and cooling ages can be correlated with the cluster's age. This allows astronomers to test the relationship between the mass of a star and the mass of the white dwarf it produces, a fundamental prediction of stellar evolution theory. The initial final mass relation, as it is called, describes how the mass of a white dwarf depends on the mass of the star that created it. A star with one solar mass produces a white dwarf with about half a solar mass, having lost the rest of its material during the red giant and planetary nebula phases. More massive stars produce more massive white dwarfs, but the relationship is not linear. The most massive white dwarfs come from stars that were just below the supernova threshold. Understanding the initial final mass relation is important for interpreting white dwarf populations. When we observe a white dwarf with a certain mass, We want to know what kind of star produced it and how long ago. The initial final mass relation provides this connection, linking the properties of dead stars to the properties of their living progenitors. The study of white dwarfs has benefited enormously from space-based observations. Telescopes in orbit can observe wavelengths of light that are blocked by Earth's atmosphere, including ultraviolet and X-ray radiation. Hot white dwarfs emit strongly in the ultraviolet, and accreting white dwarfs produce X-rays. Space telescopes have revealed populations of white dwarfs that were invisible from the ground. The Gaia space mission, launched by the European Space Agency, has revolutionized the study of white dwarfs. Gaia measures the positions and motions of over 1 billion stars with unprecedented precision, and among these are hundreds of thousands of white dwarfs. The Gaia catalog has enabled statistical studies of the white dwarf population that were previously impossible, revealing the structure and history of the Milky Way. One of Gaia's discoveries was a population of white dwarfs with unusual colors, falling between the sequences of hydrogen atmosphere and helium atmosphere white dwarfs. These objects appear to have mixed atmospheres, with both hydrogen and helium present at the surface. The origin of these mixed atmosphere white dwarfs is still being studied, but they may result from convective mixing or accretion processes. Gaia has also revealed white dwarfs with extreme velocities, moving fast enough to escape the Milky Way entirely. These hypervelocity white dwarfs may have been ejected from binary systems during supernovae or dynamically scattered from dense, stellar environments. Their trajectories provide clues about the violent events that set them in motion. The spectroscopy of white dwarfs, the detailed analysis of their light, has become increasingly sophisticated. Modern spectrographs can measure tiny features in white dwarf spectra, revealing the composition of their atmospheres with high precision. Elements present at abundances of only a few parts per million can be detected, allowing detailed studies of atmospheric pollution and accretion. Spectroscopy has revealed that many white dwarfs have magnetic fields by detecting the subtle splitting of spectral lines caused by the Zeeman effect. In strong magnetic fields, this splitting can be dramatic, with lines displaced by wavelengths far exceeding their intrinsic widths. The most magnetic white dwarfs show spectra that are almost unrecognizable. So distorted are the features by the intense fields. Time domain astronomy, the study of how objects change over time, has opened new windows on white dwarf behavior. By monitoring white dwarfs repeatedly over hours, days, or years, astronomers can detect pulsations, eclipses, transits, and other phenomena that reveal information unavailable from single observations. Large surveys that image the sky repeatedly have discovered thousands of variable white dwarfs. The discovery of transiting debris around white dwarfs has been particularly exciting. When debris passes in front of a white dwarf, it blocks some of the star's light, producing characteristic dips in brightness. The shape and depth of these dips reveal information about the size, shape, and orbit of the debris. In some cases, astronomers have watched debris disintegrating in real time, torn apart by the white dwarf's gravity. The fate of planets and asteroids around white dwarfs is a topic of active research. During the red giant phase, inner planets are typically destroyed while outer planets may survive. But what happens to the debris? Some of it falls onto the white dwarf, polluting its atmosphere. Some may form new generations of debris disks. The details of this process inform our understanding of how planetary systems evolve over stellar lifetimes. The possibility of second-generation planets forming around white dwarfs has been suggested. If enough debris accumulates in a disk around a white dwarf, it might coalesce into new planetesimals or even planets. These worlds would be fundamentally different from the first-generation planets that orbited the star during its main sequence life. No such second-generation planets have been confirmed, but the idea remains an intriguing possibility. The interactions between white dwarfs and their environments extend beyond planetary systems. As white dwarfs move through the galaxy, they occasionally pass through clouds of interstellar gas and dust. The gravity of the white dwarf can capture some of this material, leading to accretion even in isolated systems. The rates are very low, but over billions of years, even small amounts of accreted material can affect the white dwarf's appearance. Some white dwarfs have been found with compositions that are difficult to explain through normal stellar evolution. These peculiar objects may result from unusual formation channels, mergers, or interactions with companions. Each unusual white dwarf is a puzzle, inviting astronomers to develop new models and theories to explain its properties. The diversity of white dwarfs reflects the diversity of their progenitor stars and evolutionary histories. No two white dwarfs are exactly alike, even if they appear similar at a glance. The subtle differences in mass, composition, magnetic field, rotation rate, and cooling age create a population of individuals, each with its own story to tell. The naming and classification of white dwarfs has evolved over time. Early catalogs used designations based on position or discovery circumstances. Modern surveys assign systematic names based on coordinates or catalog numbers. The most famous white dwarfs: Sirius B, Procyon B, Van Maenen's star, retain their historical names, even as they are also known by catalog designations. The classification of white dwarf spectra follows a system of letters indicating atmospheric composition. Da white dwarfs show hydrogen lines in their spectra and are the most common type. Db white dwarfs show helium lines. DC white dwarfs show continuous spectra with no detectable lines, usually because they are too cool for atomic features to be visible. Other letters indicate the presence of carbon, metals, or magnetic fields. The temperature of a white dwarf is often appended to its spectral type as a numerical index. A Da4 white dwarf is a hydrogen atmosphere object with a temperature in a specific range. These classifications allow astronomers to quickly communicate the basic properties of a white dwarf without providing detailed numbers. The study of white dwarfs has a rich history stretching back over a century. The discovery of Sirius B in 1862 was followed by decades of puzzlement as astronomers tried to understand its strange properties. The development of quantum mechanics in the 1920s and 1930s provided the theoretical framework needed to explain white dwarfs, with key contributions from Ralph Fowler, Subramanian Chandrasekhar, and others. Chandrasekhar's calculation of the maximum mass of a white dwarf earned him a share of the 1983 Nobel Prize in Physics, more than 50 years after the work was done. His result was initially controversial. Sir Arthur Eddington famously dismissed it. But time and observation confirmed the correctness of Chandrasekhar's analysis. Today, the Chandrasekhar limit is a cornerstone of stellar astrophysics. The observational study of white dwarfs expanded dramatically in the latter half of the 20th century. Photographic surveys identified thousands of white dwarf candidates. which were then confirmed through spectroscopy. Space telescopes extended the observations to ultraviolet and X-ray wavelengths, revealing hot white dwarfs and accreting systems invisible from the ground. Today, the study of white dwarfs is a mature but still dynamic field. New discoveries continue to challenge and refine our understanding. The interplay between observation and theory drives progress, with each new generation of telescopes revealing phenomena that were previously beyond detection. The future of white dwarf research is bright. Upcoming space missions will survey the gravitational wave sky, detecting thousands of binary white dwarfs. Ground-based telescopes with adaptive optics will resolve white dwarf companions in nearby star systems. Spectroscopic surveys will characterize the atmospheres of millions of white dwarfs, revealing patterns of pollution, magnetism, and evolution. The James Webb Space Telescope, with its unprecedented infrared sensitivity, can observe the coolest white dwarfs with clarity impossible from the ground. These observations will extend our knowledge of white dwarf cooling to lower temperatures in older ages, approaching the realm where crystallization effects dominate the cooling curves. The Vera C. Rubin Observatory, currently under construction in Chile, will repeatedly image the entire southern sky, monitoring billions of objects for variability. Among these will be countless white dwarfs, and the survey will reveal transits, eclipses, pulsations, and outbursts in unprecedented numbers. The time-domain study of white dwarfs will enter a new era. Future gravitational wave detectors in space, such as the planned LISA mission, will open a new window on binary white dwarfs. These detectors will be sensitive to the gravitational waves emitted by thousands of binary white dwarfs in the Milky Way, providing a census of these systems that is impossible through electromagnetic observations alone. LISA will detect merging white dwarfs seconds to minutes before they collide, providing early warning for follow-up observations. The theoretical understanding of white dwarfs continues to advance as well. Computer simulations of white dwarf interiors, atmospheres, and evolution have become increasingly sophisticated. Models now include the effects of crystallization, sedimentation, diffusion, and magnetic fields, producing cooling curves of remarkable accuracy. These models are essential for interpreting observations and extracting physical information from data. The study of white dwarfs connects to some of the deepest questions in astrophysics. How do stars evolve? How do planetary systems die? What is the fate of matter in the far future of the universe? White dwarfs provide partial answers to these questions, serving as waypoints in our exploration of cosmic evolution. The patience of white dwarfs is almost beyond human comprehension. A white dwarf forming today may still be glowing billions of years from now, long after the sun has exhausted its fuel and left behind its own white dwarf remnant. The white dwarfs that exist today formed from stars that burned when the universe was young, and they will persist until the universe is inconceivably old. In their quiet persistence, white dwarfs embody a kind of cosmic endurance. They are not dramatic objects. They do not explode. They do not pulse with brilliant light. They do not dominate their surroundings. They simply exist, cooling slowly, dimming gradually, waiting patiently for a future that will take longer to arrive than the age of the universe to date. This patience is part of what makes white dwarfs so suited to contemplation. In a universe of violent births and catastrophic deaths, they offer a gentler narrative. The story of a white dwarf is not one of drama, but of duration. Not of brilliance, but of persistence. Not of fire, but of embers. As you rest, the white dwarfs continue their long cooling journeys. Somewhere in the darkness, a white dwarf that formed before the earth existed is still glowing. Its light too faint to see with the naked eye, but still present, still radiating, still patient. In another galaxy, a white dwarf is forming right now, the core of a dying red giant, beginning its billion-year journey toward the final dark. The universe is full of these quiet endpoints. For every supernova that blazes across the sky, there are countless white dwarfs cooling in silence. For every black hole that devours matter in a blaze of radiation, there are countless stellar embers radiating their heat into the void. The cosmos is not only violent, it is also patient. And in that patience, there is a kind of peace. The white dwarfs do not struggle against their fate. They do not fight the inevitable dimming. They simply radiate, cool, and persist. In their acceptance of the slow journey toward darkness, they offer a model for cosmic equanimity. The stars that became white dwarfs burned for billions of years, fusing hydrogen into helium, helium into carbon, carbon into the heavier elements. They warmed planets, perhaps hosted life, witnessed the birth of worlds and their eventual passing. And now they rest, their fires extinguished, their work complete. If you are still listening, perhaps you find some comfort in this cosmic perspective. The things that trouble us, the worries of the day, the anxieties of the future, are brief flickers against the backdrop of stellar time. The white dwarfs have been cooling since before our troubles existed, and will continue cooling long after those troubles are forgotten. You are made of atoms forged in stars. The carbon in your cells, the oxygen in your blood, the calcium in your bones, all of it was created in the nuclear fires of stars that lived and died before the sun was born. Some of those stars became white dwarfs, cooling still in the darkness, silent witnesses to the cosmic recycling that gave rise to you. In a sense, you are the white dwarf's descendants. The elements they made now live in you, animated for a brief moment, before returning to the cosmic cycle. The patience of the white dwarfs is your inheritance, written in your atoms and echoing in your cells. And perhaps that is enough. Perhaps knowing that you are part of this vast, patient, enduring cosmos is itself a kind of rest. The white dwarfs do not worry about the future. They simply exist in the present, radiating their remaining warmth into the void. You can do the same for this moment. Let your thoughts soften. Let the day's concerns drift away like the outer layers of a dying star. You need not hold on to anything, like the white dwarf releasing its envelope. You can let go and simply be. The night is long, but the white dwarfs will keep you company. Across the galaxy, across the universe, they are glowing in the darkness, patient and enduring. Their light is a whisper from the deep past, a promise that some things persist, even when the fires go out. Rest now, if you wish. The white dwarfs will still be there when you wake. The light from a white dwarf carries information encoded in its spectrum. When astronomers spread this light into its component wavelengths, they see patterns of bright and dark lines that reveal the composition, temperature, and motion of the stellar surface. Each element leaves its own fingerprint, a unique set of wavelengths where it absorbs or emits light. By reading these fingerprints, astronomers can determine what a white dwarf is made of without ever visiting it. The The spectra of most white dwarfs are dominated by hydrogen or helium, the lightest elements. This is because heavier elements sink rapidly in the intense gravitational field, leaving only the lightest elements floating at the surface. A white dwarf's atmosphere is like a perfectly stratified ocean, with the densest materials at the bottom and the lightest at the top. This stratification occurs over timescales of days to weeks, far faster than any process that might mix the layers. When heavier elements are detected in a white dwarf's spectrum, they must have arrived recently. The presence of calcium, magnesium, iron, or silicon in a white dwarf's atmosphere is a sign that something has fallen onto the star. An asteroid, a comet, or the debris of a shattered planet. These polluted white dwarfs are surprisingly common, with roughly a quarter to a third of all white dwarfs showing some evidence of heavy element contamination. The pollution of white dwarf atmospheres provides a unique opportunity to study the composition of extrasolar rocky material. When an asteroid falls onto a white dwarf, it is vaporized and mixed into the stellar atmosphere. By measuring the abundances of different elements in the atmosphere, astronomers can determine what the asteroid was made of. This is the only technique that allows direct measurement of the bulk composition of rocky bodies in other planetary systems. The results of these measurements have been remarkable. The rocky material falling onto white dwarfs appears to be broadly similar to rocky material in our own solar system, rich in oxygen, magnesium, silicon, and iron, with smaller amounts of calcium, aluminum, and other elements. Some polluted white dwarfs show evidence of water-rich material, suggesting that icy asteroids or comets are sometimes among the debris. Others show unusual compositions that hint at exotic geological processes in distant planetary systems. The most heavily polluted white dwarfs are surrounded by disks of debris, visible as excess infrared radiation from warm dust. These disks are the shattered remains of asteroids or minor planets that wandered too close to the white dwarf and were torn apart by tidal forces. The debris spreads into a ring around the star, gradually spiraling inward and falling onto the surface. These disks are direct evidence of ongoing planetary destruction caught in the act. The tidal disruption of asteroids around white dwarfs occurs at a specific distance called the Roche limit. Inside this limit, the tidal forces from the white dwarf's gravity exceed the self-gravity holding the asteroid together, and the object is torn apart. For a typical white dwarf and a rocky asteroid, the Roche limit is about 1 solar radius, close enough that the debris forms a compact disk hugging the stellar surface. The debris disks around white dwarfs are dynamic, evolving structures. Material at the inner edge of the disk spirals onto the white dwarf, while material at the outer edge may be replenished by ongoing disruption of asteroids. The disks can vary in brightness over months or years, suggesting changes in the rate of infall or the distribution of dust. Some disks appear to be transient, forming after a disruption event and then dissipating as the debris is accreted. Spectroscopic observations of debris disks have revealed that they contain gas as well as dust. The gas is produced when solid particles collide and vaporize, or when dust grains are heated to the point of sublimation. The gas orbits the white dwarf at high velocities, producing Doppler-shifted emission lines that can be used to map the structure of the disk. These observations provide a window into the physical conditions in the disk, including temperature, density, and composition. The ultimate fate of the debris is to fall onto the white dwarf and be incorporated into its atmosphere. The accretion process is continuous but variable, with rates ranging from a few grams per second to millions of tons per year, depending on the system. Over time, the accreted material sinks below the visible surface, and the atmospheric pollution fades, unless new material continues to arrive. The lifetimes of debris disks around white dwarfs are uncertain, but probably measured in thousands to millions of years. This is long enough for the disks to be observed, but short compared to the cooling age of the white dwarf. The presence of a disk indicates that planetary debris is still being delivered to the inner system, perhaps scattered inward by gravitational interactions with surviving planets. The architecture of planetary systems around white dwarfs is being revealed through these observations. The debris must come from somewhere, and that somewhere is typically the outer regions of the system where asteroids and comets survived the red giant phase. Gravitational perturbations from planets can send this debris onto orbits that bring it close to the white dwarf, where it is disrupted and eventually accreted. Some polluted white dwarfs show evidence of ongoing accretion events. Observations over months or years reveal changes in the abundances of elements in the atmosphere, suggesting that different types of material are falling in at different times. These variations provide information about the composition of individual objects being accreted, rather than just the average composition of the debris. The most dramatic evidence of planetary destruction around white dwarfs comes from transit observations. When debris passes in front of a white dwarf, it blocks some of the star's light, producing characteristic dips in brightness. These transits have been observed for several white dwarfs, revealing debris on orbits that bring it extremely close to the stellar surface. The transiting debris around white dwarfs often shows complex, variable behavior. The depth and duration of the transits can change from orbit to orbit, suggesting that the debris is not a solid body, but rather a cloud or stream of material. In some cases, the debris appears to be actively disintegrating, shedding material that trails behind in a cometary tail. One of the most studied transiting systems is WD 1145 plus 017, where astronomers have observed multiple streams of debris crossing the face of the white dwarf. The transits vary dramatically over timescales of hours to months, with new features appearing and old ones disappearing. The system is a laboratory for studying the real-time destruction of planetary material around a stellar remnant. The discovery of transiting debris around white dwarfs has opened a new field of study. By monitoring white dwarfs for transits, astronomers can identify systems with active debris disks and study the dynamics of planetary destruction. Future surveys will discover many more transiting systems, building a statistical picture of how planetary material behaves around dying stars. The presence of debris around white dwarfs raises questions about the long-term fate of planetary systems. Do all planetary systems eventually deliver material to their host white dwarfs, or only some? How long does this process continue after the white dwarf forms? What determines whether a system will be polluted or remain pristine? These questions connect the study of white dwarfs to the broader field of planetary science. The detection of water in the debris around white dwarfs is particularly significant. Water is essential for life as we know it, and its presence in extrasolar planetary material suggests that the ingredients for life may be common throughout the galaxy. If water-rich asteroids and comets existed around other stars, they may have delivered water to rocky planets, just as they did in our own solar system. Some polluted white dwarfs show chemical signatures that suggest the accreted material was differentiated, meaning it came from a body large enough to have separated into a core, mantle, and crust. These signatures include high abundances of iron relative to silicon, indicating that core material is being accreted, or high abundances of lithophile elements like calcium and aluminum, indicating crustal material. The disruption of a differentiated body would produce debris with varying compositions, which might explain the variability seen in some systems. The study of polluted white dwarfs has revealed that rocky planetary material exists around stars of all types. White dwarfs are the remnants of stars that ranged from slightly less massive than the Sun to several times more massive. The fact that pollution is common across this range suggests that rocky planets and asteroids form around a wide variety of stars, not just Sun-like ones. The pollution of white dwarf atmospheres also provides constraints on the total mass of rocky material in planetary systems. By measuring the accretion rates and the settling times of heavy elements, astronomers can estimate how much material has fallen onto a white dwarf over its cooling lifetime. These estimates suggest that some white dwarfs have accreted the equivalent of large asteroids or even dwarf planets over the course of their existence. The connection between white dwarfs and planetary science extends beyond pollution. White dwarfs can reveal information about the formation and evolution of planetary systems that is difficult to obtain any other way. The composition of accreted material reflects the composition of the original building blocks of planets, providing a window into the processes that shaped rocky worlds billions of years ago. The atmospheres of white dwarfs are not only polluted by external material, but also affected by internal processes. Convection, the bulk motion of material due to temperature differences, can mix the outer layers of a white dwarf, dredging up material from below and bringing it to the surface. This convective mixing can affect the appearance of the white dwarf and complicate the interpretation of its spectrum. In hot white dwarfs, the outer layers are radiative, meaning that energy is transported by photons rather than by bulk motion. These white dwarfs have stable stratified atmospheres where heavy elements sink rapidly out of sight. But as a white dwarf cools, its outer layers eventually become convective, and the stratification breaks down. Material that had settled below the surface can be mixed back up, changing the appearance of the spectrum. The transition from radiative to convective atmospheres occurs at different temperatures depending on the white dwarf's composition. Hydrogen atmosphere white dwarfs become convective at around 12,000 degrees, while helium atmosphere white dwarfs become convective at higher temperatures. This difference affects the evolution of white dwarf spectra and must be accounted for in models of white dwarf cooling. Convection can also affect the cooling rate of white dwarfs. When convection extends deep into the interior, it can transport energy more efficiently than radiation alone, speeding up the cooling. Conversely, a convective envelope can insulate the interior, slowing the loss of heat. The details depend on the depth and vigor of the convective zone, which in turn depend on the white dwarf's mass, composition, and temperature. The modeling of convection in white dwarf atmospheres is challenging because the physical conditions are extreme. The densities and temperatures in white dwarf envelopes are far beyond anything encountered on Earth, and the behavior of matter under these conditions must be calculated from first principles. Despite these challenges, modern models have achieved remarkable accuracy in predicting white dwarf properties. The magnetic fields of white dwarfs add another layer of complexity to their atmospheres and interiors. Magnetic fields can suppress convection, alter the transport of energy, and affect the structure of atoms at the surface. The most strongly magnetic white dwarfs may have fundamentally different atmospheric structures than their non-magnetic counterparts. The origin of white dwarf magnetic fields is not fully understood. Some magnetic white dwarfs may have inherited their fields from their progenitor stars, with the field amplified as the star contracted from red giant to white dwarf. Others may have generated their fields during mergers with companions or through dynamo processes in their interiors. The diversity of magnetic field strengths and geometries suggests that multiple formation channels may operate. The strongest magnetic fields in white dwarfs exceed 1 billion Gauss, more than 1,000,000 times stronger than any magnet created on Earth. In such intense fields, the structure of atoms is dramatically altered. Electrons are confined to move in tight helical paths along field lines, and the energy levels of atoms shift in ways that produce unfamiliar spectral features. Some highly magnetic white dwarfs have spectra that are almost unrecognizable, with features that took years to identify. The magnetic fields of white dwarfs evolve over time as the stars cool. In the fluid interior, magnetic fields can diffuse and reconnect, potentially changing strength and configuration. As the interior crystallizes, the field may become frozen into the solid lattice, preserving its structure for billions of years. The study of magnetic field evolution provides insights into the interior physics of white dwarfs. Some white dwarfs have magnetic fields that are not aligned with their rotation axes. As these stars rotate, the observed field strength and geometry change, producing periodic variations in brightness and spectrum. By monitoring these variations, astronomers can measure the rotation periods of magnetic white dwarfs and map the structure of their fields. The rotation rates of white dwarfs span a wide range from minutes to days. Newly formed white dwarfs tend to rotate rapidly, having inherited angular momentum from their progenitor stars. Over time, they spin down, though the mechanisms for this spin down are not entirely clear. Some white dwarfs in binary systems rotate synchronously with their orbital periods, tidally locked to their companions. The fastest spinning white dwarfs complete a rotation in just over a minute. These rapid rotators are thought to be the products of mergers, where the angular momentum of two coalescing stars is combined into a single, rapidly spinning remnant. The study of white dwarf rotation provides clues about their formation histories and the dynamics of binary evolution. The interiors of white dwarfs are governed by physics that differs fundamentally from ordinary matter. At the extreme densities found in white dwarf cores, electrons are squeezed so close together that quantum mechanical effects dominate. The Pauli exclusion principle prevents electrons from occupying the same quantum state, creating a pressure that resists further compression, regardless of temperature. This degeneracy pressure is what supports a white dwarf against gravitational collapse. Unlike the thermal pressure in a normal star, which depends on temperature, degeneracy pressure depends only on density. This means that a white dwarf does not need to generate energy to maintain its structure. It can cool indefinitely without collapsing. The degeneracy pressure will hold it up forever, or at least until the protons in its core decay on timescales far exceeding the age of the universe. The physics of degenerate matter was worked out in the early 20th century as part of the development of quantum mechanics. Ralph Fowler first applied quantum statistics to white dwarf interiors in 1926, explaining how electron degeneracy could support these dense objects. Subrahmanyan Chandrasekhar extended this work to include relativistic effects, calculating the maximum mass that degeneracy pressure could support. The Chandrasekhar limit of about 1.4 solar masses arises from the interplay between gravity and degeneracy pressure. As mass increases, gravity becomes stronger, compressing the white dwarf and forcing the electrons to higher energies. At the Chandrasekhar limit, the electrons would have to move at the speed of light to provide sufficient pressure, which is impossible. Above this mass, electron degeneracy pressure fails, and the star must collapse to a denser state, either a neutron star or a black hole. The existence of the Chandrasekhar limit has profound consequences for stellar evolution and cosmology. It determines which stars can end as white dwarfs and which must explode as supernovae. It sets the stage for type 1a supernovae, which occur when white dwarfs approach or exceed this limit, and it connects the quantum physics of electrons to the large-scale structure of the universe. The interiors of white dwarfs are thought to be remarkably uniform. Because degeneracy pressure does not depend on temperature, there is no strong temperature gradient driving heat flow, and the interior is nearly isothermal. The same temperature throughout. The temperature decreases only near the surface, where the matter is not fully degenerate and ordinary thermal processes take over. This isothermal interior means that the heat stored in a white dwarf is distributed throughout its volume, not concentrated in a hot core. As the white dwarf cools, the entire interior cools together, with the surface acting as a bottleneck that limits how fast energy can escape. The cooling rate depends on the properties of this surface layer, including its composition and opacity. The thin outer layer of a white dwarf, where matter transitions from degenerate to non-degenerate, is called the envelope. This envelope contains only a tiny fraction of the star's mass, but plays a crucial role in determining its appearance and cooling rate. The envelope acts as an insulating blanket, regulating the flow of heat from the interior to the surface. The structure of the envelope depends on its composition. Hydrogen-rich envelopes are relatively opaque, trapping heat and slowing the cooling of the white dwarf. Helium-rich envelopes are more transparent, allowing heat to escape more easily. This is why hydrogen atmosphere white dwarfs tend to be warmer than helium atmosphere white dwarfs of the same age. Their envelopes insulate them more effectively. The mass of the envelope is extremely small, only about 100,000th of the star's total mass for hydrogen-rich envelopes, and even less for helium-rich ones. Yet this tiny amount of material has a disproportionate effect on the white dwarf's evolution. Models of white dwarf cooling must treat the envelope carefully to produce accurate predictions. Some white dwarfs have lost their hydrogen envelopes entirely, exposing the helium layer beneath. These helium atmosphere white dwarfs may have lost their hydrogen through stellar winds, nuclear burning, or interactions with companions. Without the insulating hydrogen layer, they cool faster and appear different from their hydrogen atmosphere counterparts. The evolution of white dwarf atmospheres over time is complex. As a white dwarf cools, various processes can change the composition of its surface layers. Convection can dredge up material from below. Accretion can deposit material from above. Diffusion can separate elements by weight. Radiative levitation can suspend certain elements in the atmosphere against the pull of gravity. All of these processes interact, producing the diversity of white dwarf spectral types observed today. Radiative levitation is particularly important in hot white dwarfs. Photons streaming outward from the hot interior can transfer momentum to atoms in the atmosphere, pushing them upward against gravity. Different elements experience different amounts of levitation depending on their atomic properties, leading to selective enrichment of certain species. This process can explain why some hot white dwarfs show traces of heavy elements that would otherwise sink out of sight. As white dwarfs cool below about 20,000 degrees, radiative levitation becomes ineffective, and gravitational settling dominates. Heavy elements sink rapidly out of the atmosphere, leaving only hydrogen or helium at the surface. This transition marks a change in spectral type for many white dwarfs, as the metals that were visible in the hot phase disappear in the cool phase. The interplay between these atmospheric processes creates a complex picture of white dwarf evolution. A white dwarf that appears one way at a young age may look quite different as it cools. Predicting these changes requires detailed models that account for all the relevant physics, from the quantum mechanics of degenerate matter to the atomic physics of radiative transfer. The study of white dwarf atmospheres has practical applications beyond pure astrophysics. White dwarf spectra serve as calibration standards for astronomical instruments, providing well-understood sources of light across a wide range of wavelengths. The most stable white dwarfs, with predictable spectra and minimal variability, are used to calibrate the sensitivity and wavelength accuracy of spectrographs and cameras. White dwarfs have also been proposed as fundamental flux standards, objects whose brightness is known with high precision, and can be used to calibrate measurements of other sources. By comparing observations of other objects to white dwarf standards, astronomers can determine absolute brightnesses and correct for instrumental effects. This application requires precise modeling of white dwarf atmospheres, which has driven improvements in atmospheric theory. The temperatures of white dwarfs can be measured with remarkable accuracy using spectroscopic techniques. By fitting model spectra to observed spectra, astronomers can determine effective temperatures to within a few percent. These measurements, combined with distances from parallax observations, allow the luminosities and radii of white dwarfs to be calculated. The consistency of these measurements with theoretical predictions provides strong confirmation of our understanding of white dwarf physics. The masses of white dwarfs can be determined through several techniques. In binary systems, the gravitational interactions between the white dwarf and its companion reveal the masses of both objects. For isolated white dwarfs, the mass can be inferred from the gravitational redshift of spectral lines, the shift in wavelength caused by photons climbing out of the star's gravitational well. This technique requires high-quality spectra, but has been successfully applied to hundreds of white dwarfs. Another technique for measuring white dwarf masses uses the mass-radius relationship. By measuring the radius independently, through eclipse observations, interferometry, or other techniques, and combining this with theoretical predictions for how radius depends on mass, astronomers can infer the mass. This approach relies on the accuracy of the theoretical mass-radius relationship, which has been well tested for white dwarfs. The distribution of white dwarf masses provides insights into stellar evolution. Most white dwarfs have masses close to 0.6 solar masses, reflecting the typical outcome of low-mass stellar evolution. There is a tail of higher-mass white dwarfs extending up toward the Chandrasekhar limit, produced by more massive progenitor stars. And there are some low-mass white dwarfs, below about 0.45 solar masses, that cannot have formed through single-star evolution in the age of the universe. They must be the products of binary interactions. These low-mass white dwarfs are sometimes called helium-core white dwarfs because they likely consist primarily of helium rather than carbon and oxygen. They form when a star loses its envelope before helium fusion can begin in the core, leaving behind a helium-dominated remnant. This typically occurs in close binary systems, where the companion strips away the envelope through mass transfer. Helium-core white dwarfs cool differently than carbon-oxygen white dwarfs because of their different compositions. Helium has different thermal properties than carbon and oxygen, affecting the cooling rate and the onset of crystallization. Some helium-core white dwarfs may experience shell flashes, brief episodes of hydrogen fusion in a thin shell around the core, that temporarily brighten the white dwarf and complicate its cooling history. The diversity of white dwarf masses and compositions reflects the diversity of their progenitor stars and evolutionary pathways. By studying the population of white dwarfs, astronomers can learn about the lives and deaths of stars across a wide range of initial conditions. Each white dwarf is a data point in this cosmic census, contributing to our understanding of stellar evolution. The surface gravities of white dwarfs are extraordinarily high, typically around 100,000 times Earth's surface gravity. This intense gravity has profound effects on the structure of matter at the white dwarf's surface. Atoms are squeezed into their lowest energy states. Molecules are crushed and dissociated. The scale height of the atmosphere, the distance over which pressure decreases by a factor of E, is only a few hundred meters compared to kilometers for a normal star. This compressed atmosphere means that the photosphere of a white dwarf, the layer from which light escapes, is extraordinarily thin. The entire visible surface is contained within a layer less than a kilometer thick. Below this layer, the matter is so opaque that photons cannot escape directly. They must be re-emitted multiple times before finally reaching the surface and streaming into space. The high surface gravity also affects the spectral lines observed from white dwarfs. The pressure at the photosphere is so high that atoms are constantly colliding, broadening the spectral lines through a process called pressure broadening. The hydrogen lines in white dwarf spectra are characteristically broad and smooth, quite different from the sharp lines seen in lower gravity stars. This broadening is actually useful. It allows the surface gravity to be measured from the spectrum, independent of other techniques. The combination of temperature and surface gravity determines the spectral appearance of a white dwarf. Hot, high-gravity white dwarfs have broad, shallow hydrogen lines. Cool, lower-gravity white dwarfs have narrower, deeper lines. By measuring the shapes of these lines, astronomers can determine both the temperature and the gravity, and from the gravity, the mass. This technique, called spectroscopic fitting, is one of the primary methods for characterizing white dwarfs. The atmospheres of white dwarfs are remarkably simple compared to those of other stars. Because only the lightest elements remain at the surface, the chemical complexity is minimal. There are no molecules to worry about, no forests of overlapping lines from dozens of species. The simplicity of white dwarf atmospheres makes them easier to model accurately, which is why they serve so well as calibration standards. Despite this simplicity, white dwarf atmospheres still hold surprises. Some white dwarfs show magnetic field strengths that vary across the surface, creating patches of different spectral appearance. Others show chemical spots where certain elements are concentrated by magnetic fields or other processes. A few white dwarfs pulsate, with their atmospheric properties varying over the pulsation cycle. The simplicity is relative. There is still much to learn. The space velocities of white dwarfs, their motions through the galaxy, provide information about their ages and origins. White dwarfs that formed in the thin disk of the Milky Way tend to have relatively low velocities, moving on nearly circular orbits around the galactic center. White dwarfs from the thick disk have higher velocities and more elliptical orbits. White dwarfs from the halo have the highest velocities of all, tracing elongated orbits that carry them far from the galactic plane. By measuring the velocities of white dwarf populations, astronomers can determine which stars belong to which galactic component. This kinematic classification provides an independent check on age estimates derived from cooling. Halo white dwarfs should be old, and indeed they are. They have low temperatures and luminosities consistent with billions of years of cooling. Some white dwarfs have velocities so high that they cannot be bound to the Milky Way. These hypervelocity white dwarfs are traveling fast enough to escape the galaxy entirely, destined to wander intergalactic space forever. They may have been ejected from binary systems during supernova explosions, or dynamically scattered from the galactic center through interactions with the central black hole. The study of hypervelocity white dwarfs connects stellar astrophysics to galactic dynamics. By tracing their trajectories backward in time, astronomers can identify where they originated and what events set them in motion. These cosmic runaways are messengers from extreme environments, carrying information about conditions in the places they left behind. The local neighborhood of the Sun contains hundreds of known white dwarfs within a few hundred light years. These nearby objects are the best studied with the most precise measurements of temperature, mass, composition, and velocity. They serve as benchmarks for understanding more distant populations. The nearest white dwarfs are close enough that their proper motions, their apparent movement across the sky, are easily measurable. By tracking these motions over years or decades, astronomers can determine the three-dimensional velocities of white dwarfs and trace their past and future trajectories. Some nearby white dwarfs will pass even closer to the Sun in the future, while others will recede into the distance. The solar neighborhood white dwarf sample has been used to estimate the local density of white dwarfs. By counting how many white dwarfs are found within a given volume and correcting for incompleteness, astronomers can determine how many white dwarfs per cubic parsec are expected. This local density, combined with models of the galactic distribution, allows estimates of the total number of white dwarfs in the Milky Way. Current estimates suggest that the Milky Way contains roughly 10 billion white dwarfs. This is comparable to the number of stars currently fusing hydrogen in their cores, meaning that roughly half of all stellar objects in the galaxy are dead or dying. The galaxy is a vast cemetery of stellar remnants, with white dwarfs among the most numerous occupants. The light from all these white dwarfs contributes to the background glow of the galaxy, though their individual faintness means this contribution is small compared to living stars. In the far future, when star formation has ceased, and most stars have evolved off the main sequence, white dwarfs will dominate the stellar mass budget of the galaxy. They will be the primary stellar population, cooling slowly in a dimming cosmos. The connection between white dwarfs and the future of the galaxy leads naturally to questions about the far future of the universe. What will happen to white dwarfs as cosmic time stretches on? How will they interact with the changing conditions of an aging cosmos? These questions take us to the edge of known physics and into the realm of speculation. In the short term, over the next few billion years, white dwarfs will continue to form as sun-like stars exhaust their fuel. The population of white dwarfs will grow, even as individual white dwarfs cool and fade. The rate of white dwarf formation depends on the rate of star formation in the past, which has been declining since its peak several billion years ago. Eventually, the formation of new white dwarfs will slow to a trickle as the raw materials for making new stars are exhausted. On longer timescales, the Milky Way will merge with the Andromeda Galaxy, forming a larger elliptical galaxy. This merger, expected in about 4 to 5 billion years, will scramble the orbits of stars and white dwarfs alike. Some will be flung into intergalactic space. Others will be drawn closer to the merged galaxy's center. The eventual distribution of white dwarfs in the merger remnant will reflect the violence of the collision. After the merger, star formation will continue for a time, fueled by gas compressed during the collision. But eventually, the gas will be used up or heated to the point where it can no longer collapse into stars. The last stars will form, live their lives, and die, adding their white dwarfs to the growing population of remnants. When the era of star formation ends, no new white dwarfs will form. The population will be fixed, and all that will remain is the slow cooling into darkness. The timescale for all white dwarfs to cool into black dwarfs is staggering. Even the fastest cooling white dwarfs require tens of billions of years to fade to invisibility, and the slowest cooling ones may take over 100 billion years. By comparison, the universe is currently only about 14 billion years old. The era of black dwarfs lies far in the future, beyond any foreseeable astronomical observation. During this cooling era, the universe itself will be changing. The expansion of space will continue, driven by dark energy. Galaxies will recede from each other, eventually passing beyond each other's cosmic horizons. The merged Milky Way Andromeda Galaxy will become an island universe, isolated in a vast and emptying void. The white dwarfs within it will cool in cosmic solitude, their light reaching no distant observers. As the white dwarfs cool, their internal structures will continue to evolve. Crystallization will complete, transforming the entire interior into a solid lattice. The crystals will be nearly perfect, with defects annealed out over billions of years of atomic rearrangement. The white dwarf will become a single giant crystal floating in space. The temperatures of the oldest black dwarfs will approach the temperature of the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. At that point, the black dwarfs will be in thermal equilibrium with the universe itself, no warmer than their surroundings. They will emit no net radiation, absorbing and emitting photons at exactly the same rate. They will be invisible, not because they emit no light, but because they are no brighter than the background. Even this equilibrium will not last forever. The cosmic microwave background is cooling as the universe expands. its temperature dropping inversely with the scale factor of the cosmos. Eventually, the background will be colder than even the oldest black dwarfs, and the remnants will once again stand out against the darkness. Though by this point, the differences will be infinitesimally small. On truly extreme timescales, the matter in black dwarfs may undergo exotic transformations. If protons are unstable, as some theories suggest, they will eventually decay, converting the mass of the black dwarf into radiation and lighter particles. The timescale for proton decay is at least 10 to the 34th years and probably much longer, incomprehensibly vast compared to the current age of the universe. But given enough time, even protons may not be eternal. If proton decay occurs, black dwarfs will slowly evaporate, their mass dwindling over eons as protons and neutrons decay into positrons, neutrinos, and photons. The end state would be a diffuse cloud of radiation and leptons, dispersing into the void. The black dwarf would cease to exist as a coherent object, its matter returned to the universe in the most fundamental way possible. If protons do not decay, black dwarfs may persist indefinitely as solid lumps of matter drifting through an eternal cosmos. Occasionally, two black dwarfs might collide in the darkness, merging in a flash of energy before settling back into cold silence. More rarely still, quantum tunneling effects might cause the nuclei in a black dwarf to fuse, reigniting nuclear reactions in a burst of unlikely chemistry. But these events would be separated by timescales so long that they are difficult to express in human terms. The contemplation of these far future scenarios is humbling. The universe that gave rise to stars and planets and life will eventually become a cold, dark, nearly empty void. The white dwarfs that now cool quietly in the galaxy are the first step on this long journey into darkness. They are the harbingers of a future in which matter itself may not be permanent. And yet there is something peaceful in this vision. The end is not violent. It is gentle. The white dwarfs do not rage against the dying of the light. They accept it, cooling slowly, fading gracefully, persisting for as long as the laws of physics allow. Their patience is absolute, their endurance unmatched. In a universe of change, they represent a kind of constancy. The story of white dwarfs is, in the end, a story about endings, but it is also a story about persistence. The white dwarfs forming today will outlast the stars that created them, outlast the galaxies that host them, outlast perhaps even the atoms of which they are made. They are the long goodbye of stellar evolution, the slow fade that follows the brilliant life. And in that fade, there is beauty. The light of a white dwarf has traveled across space to reach us, carrying information about conditions at the stellar surface. Each photon is a messenger, a tiny packet of energy released by a cooling ember, billions of years old. When we observe white dwarfs, we are witnessing the afterglow of fires that burned before the Earth existed. The photons that reach your eyes tonight, if you are still awake, left their sources long ago. The light from Sirius B, the nearest white dwarf visible to modest telescopes, departed about 8.5 years ago. The light from more distant white dwarfs may have been traveling for centuries or millennia. You are seeing the past, frozen in light, delivered across the void. This is true of all astronomical observation, of course. Light takes time to travel, and so we always see the universe as it was, not as it is. But with white dwarfs, the effect is particularly poignant. These are objects that have already died, in a sense, their nuclear fires extinguished, their active lives complete. The light we receive is the afterglow, the lingering warmth of stars that burned out long ago. Yet the white dwarfs themselves are still there, still cooling, still persisting. The object that emitted the light we see tonight is still glowing. 8 or 80 or 8,000 years further along in its cooling journey, the universe contains an unbroken chain of light connecting the past to the present, a continuous stream of photons linking the moment of emission to the moment of observation. In this sense, observing white dwarfs is a form of communion with the past. We are receiving messages sent by ancient stars, signals that have survived the journey across interstellar space. The information in that light, the temperature, the composition, the magnetic field, is a gift from objects that have been cooling since before human history began. The study of white dwarfs is also a confrontation with the future. When we model the cooling of white dwarfs over billions of years, we are projecting ourselves forward in time, imagining a universe that no human will ever see. The calculations are precise, the physics well understood, but the timescales involved dwarf all human experience. We are visitors in a cosmic story that will continue long after our species is gone. And yet, there's comfort in knowing the story. The universe is not arbitrary. It follows rules, patterns, laws that can be understood and predicted. The white dwarfs will cool according to these laws, regardless of whether anyone is watching. The future of the cosmos is not random, but determined in its broad strokes by the physics that governs matter and energy. This predictability is a kind of assurance. The universe will continue, even if we do not. The white dwarfs will keep cooling. The black dwarfs will eventually form. The cosmos will evolve toward its final state. There is no need to worry about the outcome. It is already determined, already unfolding, already in motion. The anxiety of the unknown is replaced by the peace of the inevitable. The white dwarfs do not fear their fate. They are not conscious, of course. They are balls of dense matter cooling in the void. But if they were capable of something like acceptance, they would embody it. They do not struggle against the cooling. They do not try to reignite their fires. They simply radiate, slowly and steadily, releasing the heat stored from billions of years of nuclear fusion. Perhaps there is something to learn from this. The white dwarfs have achieved what we might call equanimity, a state of calm acceptance in the face of inevitable change. They are not troubled by the future because they are wholly present in the moment, radiating their warmth into the universe without grasping or resistance. This is not to say that white dwarfs are wise in any meaningful sense. They are physical objects, governed by physical laws without inner lives or intentions. But the patterns they follow, the slow release, the gradual fading, the patient persistence, can serve as metaphors for a certain kind of peace. In contemplating white dwarfs, we contemplate a mode of being that is calm, enduring, and accepting. The night is advancing now, and perhaps you are approaching rest. The facts about white dwarfs have flowed past like lights in the darkness, some noticed and some not. That is fine. The purpose of this journey was not to memorize every detail, but to drift along, carried by the current of wonder toward whatever shore awaits you. The white dwarfs will still be there tomorrow and the day after, and for billions of days to come. They are patient. They do not demand your attention. They simply exist, glowing softly in the void, available to anyone who cares to look. The universe is filled with their gentle light. You are made of the same elements that white dwarfs are made of: carbon, oxygen, hydrogen, traces of heavier things. These elements were forged in stars, scattered by stellar deaths, gathered into planets, and eventually into you. The matter in your body has been part of stars, part of interstellar clouds, part of the cosmic web of gas and dust that fills the galaxy. Someday, the sun will become a white dwarf. The process will take billions of years, and by then, the Earth will be long transformed. Perhaps engulfed, perhaps scorched, certainly unrecognizable. The solar system will contain a white dwarf where the sun once shone, a small dense remnant surrounded by whatever planets and debris survive the transition. The atoms that make up your body will by then have dispersed, returned to the cosmos through the cycles of nature. Some may be incorporated into new stars, new planets, new living things. Others may drift through interstellar space, cooling in the darkness like microscopic echoes of the white dwarfs above. The elements persist, even if the forms they take are temporary. This is the great recycling of the cosmos. Stars form, burn, die, and scatter their elements into space. New stars form from the enriched material, burn, die, and scatter more. Each generation of stars adds to the cosmic inventory of heavy elements, building toward a universe where planets and life become possible. You are a product of this cosmic alchemy, assembled from stardust over billions of years. The white dwarfs are part of this cycle. They are the remnants of stars that contributed to the enrichment of the cosmos, the cooling embers of fires that forged elements and scattered them into space. The light they emit now is a final contribution, a last gift of energy to the universe before they fade into darkness. And so the story comes full circle. The white dwarfs that now cool in the galaxy were born from material that was itself produced in earlier generations of stars. They are children of the cosmos, shaped by the same processes that shaped the sun and the earth and you. Their fate is the fate of all stellar matter: formation, burning, death, dispersal, renewal. This cycle will continue for as long as the universe allows. New stars are forming now, in nebulae scattered across the Milky Way. Some of them will become white dwarfs in a few billion years. Others will explode as supernovae, seeding space with heavy elements. The cosmic dance of creation and destruction goes on, indifferent to human observation, but open to human wonder. As you rest tonight, you are part of this dance. Your breath draws in atoms that have been part of countless other beings. Your heartbeat is powered by energy that traces its origin to the nuclear furnace of the sun. You are a temporary arrangement of matter and energy, a brief eddy in the cosmic flow, beautiful and impermanent. The white dwarfs remind us of this impermanence, but they also remind us of persistence. Even as they fade, they endure. Even as they cool, they remain. The universe is not only a place of change, but also a place of continuity. The laws of physics that governed the first white dwarfs still govern the white dwarfs forming today. The patterns repeat, the cycles continue, the cosmos goes on. And now, perhaps, it is time for you to drift into your own small rest. The white dwarfs will keep their vigil while you sleep, glowing softly in galaxies near and far. They ask nothing of you. They offer their light freely to anyone who cares to receive it. Let your breath slow. Let your thoughts soften. Let the day's concerns dissolve like the outer layers of a dying star. drifting away into space. You need not hold on to anything. The universe will continue without your effort, as it always has, as it always will. The white dwarfs are patient. They have been cooling for billions of years, and they will continue for billions more. A single night's rest is nothing to them. A flicker, a moment, barely a pause in their long journey toward darkness. But for you, it is precious. Let yourself receive it. If you're still awake, you can continue to the next video now. The gentle facts will be waiting for you whenever you are ready. There is no rush. The cosmos is patient, and so are we. But if sleep is calling, let it come. Let your eyes close. Let your body relax into the support beneath you. Let the thoughts of white dwarfs and cooling embers in cosmic time drift away like clouds across a darkening sky. You are safe. You are held by the same gravity that holds the planets in their orbits and the stars in their galaxies. You are part of something vast and old and beautiful, something that began long before you were born and will continue long after you are gone. There is nothing you need to do, nowhere you need to be, nothing you need to become. You are already complete, already part of the cosmic whole. Sleep well, dream softly, and know that somewhere in the darkness, the white dwarfs are glowing, patient and enduring, keeping watch over a universe that has all the time it needs. Good night.